Hello, everybody. So, dear distinguished speakers, dear participants, dear colleague, friends, on behalf of the Brazilian InterPore chapter, it's my great pleasure, with my great enthusiasm, to welcome you to our last section. Last but surely not least, of our fourth InterPore Brazilian chapter meeting. Again, I would like to thank all the participants from Brazil and abroad too. And so let me highlight a little bit the afternoon of our section. I'd like to thank each one of our invited speakers for agreeing to take time of your busy schedules to give us perspective on Porous media Microfluidics. It is a complex topic. Recent improvements on the fabrication techniques of microfluidic device have led to a growth in the use of flow visualization, for instance, at a pore scale to gain specific information on how different phases occupy the pore scale. In this section, our invited speaker will discuss recent advances on the use of microfluidics to gain fundamental understanding and comprehension on pore scale flows of complex fluids. Our four speakers are, first, Márcio Carvalho from PUC here in Brazil, Suji Data, sorry if I'm not pronounced the correct way, from Princeton University. Many thanks for your coming, many thanks. Aurora Pérez from PUC, Rio de Janeiro, and Fabiano Wolff from Federal University of Santa Catarina, Joinville. So let's start with our first speaker. Márcio, the word is yours. Many thanks.
Well, thank you, Eduardo. I'm just going to share my screen. Can you see my screen now?
Yes, please, okay. Go ahead.
Okay, so good afternoon or good evening, depending where you are. I'd like to first thank the organizer to invite me to give this talk. And I'll talk about microscale physics during oil displacement used with complex liquids. I left here my email, so if you have any questions also, you can contact me after the talk. Okay, so when you're, most of the application I'm going to talk about here is going to be related with oil recovery. So typically when you're trying to recover oil from a reservoir, you need to displace it towards the producing well. And then the amount of oil that you're able to recover, it's going to be a function of how well or how uniform you're able to macroscopically displace the oil in the reservoir, but also how well you're able to displace the oil in the areas where the water have reached in the reservoir. And typically, even in the areas where the water has reached in the reservoir, there's still a lot of oil that gets trapped by capillarity in the pore space. So just highlighting here one schematic view of what's going on in the pore scale, the water may flow through some pores and leave an oil ganglia trap. This oil ganglia is trapped by capillarity. And the way to displace this oil ganglia is that if the pressure difference that's acting in the both ends of the oil ganglia has to be larger than the capillary pressure. So if we want to reduce the residual oil saturation or the amount of oil that gets trapped by capillarity, you can do two things just looking at this equation. We can reduce the right-hand side by, for example, lowering the interfacial tension, or you can increase the left-hand side of this equation in order to mobilize. Okay, so this is what we're going to be focusing more. How can we change the pressure difference of the water phase due to some nonlinear flow behavior in order to displace this trapped oil ganglia and reduce residual oil saturation? So we can change this pressure difference in the water flow by injection of complex fluids, and there are many options that you can follow: surfactant solution, polymer solutions, emulsions, and foams. I'm going to focus my talk here in the emulsions and foams topic. In the morning, Yulia talked a little bit about flow of polymer solutions, and Sujit is going to talk about in more details polymer in the next talk. So the point is that if you want to try to probe and analyze this problem with all these different complex fluids, you can do coarse scale tests which are long and expensive, but you have great potential of using microfluidics and pore scale modeling and visualization to understand the underlying physical mechanism, and then from there try to optimize the injection process. So this is going to be the goal of this talk. So I'm going to give two examples of work that we have been doing in our lab in the last, I would say, 3 years or so. One is associated with the flow of suspensions of microcapsules, and the other one is associated with foam. So these are complex fluids that are injected or can be injected in a reservoir to try again to change the pressure distribution in the water phase and mobilize the oil ganglia. So the first story is associated with the suspension of microcapsules. This has been work of many collaborators. Bruna just finished her PhD thesis. Mariano was a postdoc in the lab. He's now a professor at Rio Grande do Sul. Jose Roque also finished recently his PhD thesis, and Rafael finished also his master's thesis. So the basic idea is that, playing this cartoon movie here, I apologize for some of the Portuguese, but if you're injecting water to displace the oil, so the water would create a preferential path. So now all the water is flowing this blue area, and all the black area, which are the pores occupied by the oil phase, the oil there is trapped. So if you want to mobilize this oil, is that you try to block the water flow using some sort of a dispersed phase in the water phase. So if the pressure that you need to make this dispersed phase flow through a constriction gets too high, water gets diverted to oil-containing pores. So you're able to displace oil this way. So we need to understand and control the degree of pore blocking by getting this flow divergence mechanism associated with the water flow. So this idea is not new. So emulsion has been successfully used as flow mobility control. So this is an old paper from the early 70s of a reservoir field scale test done by Chevron in the United States. So the continuous line is oil production. You can see as time goes by, the oil production is going down. During some here in the middle of 1966, they injected in one water injection well, they injected oil in water emulsion, so very small oil drops dispersed in water, and then followed by a continuing water injection. You can clearly see that the oil production went up, and then they went back just injecting water. You can see now that the production is going down, but you have all this extra volume of water of oil that was produced. Okay, so since then a lot of tests and experiments have been done looking at this emulsion flow. We've done a lot of work on this in the lab, maybe in the last 10 years or so. So here's just one example of the flows of the studies that we've done. This was a core flooding test in a sandstone. So we inject water. The blue line here is oil production. So after around 5 pore volumes of water injection, we were not producing any oil anymore. So the recovery factor was around 33%. The red line is injection pressure. It came to a point that we stopped injecting water and started injecting emulsion, basically very small oil drops dispersed in water, very low concentration. You can see that the pressure went up because now I need to force the drops of the emulsion to flow through the pore throats. And then we stopped injecting emulsion, went back injecting water, the pressure went down, and you can see that the recovery factor went from 33 to 40, and then we repeat the cycle, went back up to 55%. So injecting a dispersion may work as a flow divergent agent and able to recover more oil. One important point is that the degree of pore blocking of mobility change is associated with how hard it is for the dispersed phase to flow through a pore throat. If you're using emulsion, you have very little control of this force, because basically you could play around with the interfacial properties of an oil drop, but you don't have a lot of control on that variable. You can maybe change the viscosity of the oil that you're injecting, but again, you don't have a lot of room for that. So that's why when we started looking at going from this emulsion flooding, but instead of having oil drops, maybe having microcapsules with a polymeric shell instead of just an oil drop, because then we could play around with the properties of this with this polymeric shell, making it softer or harder, depending on if we wanted to have a very strong or a stronger or a weaker pore blocking effect. So the first challenge was to produce monodispersed microcapsules, and we want to use biopolymers such that we could inject that in reservoirs without any environmental issue. So we use microfluidics using the technique that was described by Utada et al. This glass capillary microfluidics. It's basically, you have a three-phase flow such that you form a double emulsion template. And then this middle phase is going to be a polymeric phase that you're going to cross-link the polymeric phase to form a solid phase. So here's just a video of the producing process. You have to have the right conditions in order to get to this dripping flow regime. You can see that all the double emulsions are all the same size. So it's a very monodispersed system. So it's easy to control the properties. Here's just a bird's eye view of the entire process. In this case, the inner phase was dyed with this color such that we could just visualize what's going on. So once you get it to the right condition, you're producing all these capsules that are exactly the same size. And then you collected them, and then that's what we use to inject in the porous medium. So this was part of Bruna's thesis. She published a paper on the fabrication of these capsules. The first thing, the important thing was to look at in the operability parameters of this flow, what's the region at which we produce these monodispersed microcapsules. So if you're outside this shaded area, you're going to have some type of defect that we are not interested in on this. So basically, we are getting a feasibility window of production of microcapsules. And once we are inside this window, we can control both the diameter of the microcapsules and also the thickness of the shell by playing around with the flow rates or geometry of the microfluidic device. So in a sense, we can make capsules of different sizes and also capsules of different stiffness, because we can control the degree of cross-linking of the polymer and also the thickness of the shell. And then the rigidity of the capsule is going to be proportional to the cubic power of the thickness. So if I want a very rigid shell, I can have a thicker shell. If I want a less rigid or a more soft capsule, I can have a very thin shell. So we learn how to do that. So the next step was, okay, how hard it is, or can we control the mobility change or the pore blocking effect with these microcapsules? So what type of properties do I need in the microcapsules to get the right pore blocking effect? Okay, so we published this earlier this year. The idea was we get the microcapsules that we produce. Now we flow it through a constricted capillary, and then we measure the pressure difference of the flow. Okay, so in this case, we have this constricted capillary with a 100 micrometer throat and a 300 micrometer diameter. And then we flow different capsules through this constriction, measuring the pressure difference. And we flow at a constant flow rate here of 0.2 milliliters per hour. So we made different capsules with different shell thickness and different diameters. So I won't go a lot on the details, but what I want to highlight here is that this flow is governed by these dimensionless parameters. So the dimensionless diameter of the capsule. So this is a ratio of the capsule diameter to the constriction diameter. So if the capsule is smaller than the constriction, we will flow much easier than if it's larger than the constriction. And the higher is the size of the capsule, the harder it is to flow through a constriction, because it will have to squeeze a lot to go through that constricted channel. The surface capillary, it's kind of like a capillary number, but instead of having a surface tension in the denominator, you have the elastic modulus of your polymeric shell. So if I want to have if I have a very rigid shell, it means that I will have a very low surface capillary number. So again, the interfacial forces are going to be more and more important. So we with all these systems that we made, we were basically changing this capsule diameter, the dimensionless capsule diameter, and also the surface capillary diameter that we changed. We didn't play around with the polymer that we were using or the degree of cross-linking, but we changed the thickness of the shell. So by changing the thickness of the shell, we were changing the modulus of the shell. So here's just an example of a capsule flowing through a constriction. I'll play the video here. You're going to see the capsule. It needs to deform to flow through. As it deforms, the pressure goes up. So we have a syringe pump where we are keeping a constant flow rate. Up to a point that the pressure gets high enough, that's strong enough to force the capsule to flow through the constriction, and then the pressure goes down. Okay, so we know there is like a mobility change. There is a a value of the pressure difference that we need in order to make that capsule to flow. If the pressure difference in that pore throat is smaller than this value, the capsule will block that pore throat. So that's the basic idea. So we try a different system. So in this case, the capsule diameter was 1.44 of the throat diameter. So we flew a larger capsule here, 1.75. So now this is a larger capsule. The behavior seems to be the same. The capsule gets stuck in there, but now this is a larger capsule. It needs to deform more in order to be able to flow through the constriction. The pressure goes up more and more and more, but the pressure gets so high, and then you're deforming the shell of the capsule so much that at the end, this takes a while. Let me advance here the video. It will happen soon, but you can see here in the pictures, the force that's acting in the membrane gets so strong that the membrane ruptures, and then the internal content of the capsule escape. So this would not be a good capsule for mobility control because you're destroying the capsule during the flow. So this is another issue that we need to pay attention to. So we need to design capsules that will block the pore. You see now in the movie, the capsule just burst. So what Bruna did was to map in this operability parameter of surface capillary number and size of the capsule, where you can have flow where the capsule does not release its inner content, so the capsule is not burst. So we need to be in this area here below this shaded area, this shaded line, in order to get the mobility control to work. Okay, so depending on, again, the surface capillary number or the size of the capsule with respect to the pore throat, we would get different levels of pore blocking. If we go above this line, this would not be a good capsule to inject in the porous media, because basically we would just burst these capsules and lose its property of pore blocking. So in order to design this, the appropriate capsules for the level of pore blocking that's needed in different situations, we could run more and more experiments, but that would be extremely costly and time consuming. So José Roca developed a model to try to study this problem. So the idea is to have a numerical simulation where we are going to study the flow of a Newtonian liquid flowing with a suspended capsule. And then we want to study how the pressure difference changes as this capsule flow through the constriction. And then with that, we could design or obtain what's the pressure drop increase as a capsule is flowing through this constriction, and how that pressure drop changes as we change the properties of the shell of the capsule. So we combine finite element methods with immersed boundary methods. So the liquid flow is described, is solved, or the Navier-Stokes equation for incompressible flow is solved using regular finite element method, but we include the deformation of the shell in an immersed boundary type solution. So we have to include an extra force here, which is the interaction between the solid phase and the liquid phase. And then the solid phase here is described by a one-dimensional mesh that is convected through the fixed Eulerian mesh that we use to solve the fluid flow. And then all the solid mechanics equation is discretized in this one-dimensional mesh of the immersed boundary methods. I won't go into the detail of the mathematical formulation here for the sake of time, but just showing some results. So here we have initially, there's no flow. The velocity is 0. Here's the pressure field. So the pressure is constant. The pressure in the liquid inside the capsule is higher because the capsule is pre-tension. So there is a tension on the membrane. So by kind of like a capillarity action, the pressure in the concave side is higher than the pressure in the convex side. That's why we have this higher pressure inside the capsule. So now we're going to start the flow. We are going to impose a flow rate. I'll stop here. You see that the capsule is flowing through the constriction, going back here. You can see now there is a pressure difference. As the capsule is going to flow through the constriction, the pressure difference is going to get higher and higher. And this middle plot is showing the pressure difference from the inlet to the outlet. You can see that as the capsule is flowing through the throat, the pressure will go up. And then as the capsule gets out of the throat, the pressure will go down, reaching again the steady state. So we are able to model what is the extra pressure that I need to make that capsule flow through the constriction. And then I can run this for different capsule properties. I can change the stiffness of the membrane or the shell, and to see how I can control this extra pressure depending on the properties of the shell. So this is what's shown in this plot. So the continuous black line would be a limiting solution for an infinite capillary number. So basically a shell that has no mechanical stiffness at all. So this would just be a single phase flow. There's no extra pressure. There's no resistance for the capsule to flow through the constriction. As we make the capsule more and more rigid, we are making the capillary number smaller and smaller. And then you can see that the pressure peak increases as the capillary number goes down. So I need a stronger pressure difference to make that capsule flow through that constriction. So we can map that, the ratio of the delta P of the continuous flow divided by the maximum delta P. This would give us an idea of how much pore blocking effect or mobility control we are getting with the capsule. And then we can get a plot of that as a function of the size of the capsule and also as a function of the surface capillary number. So we can use a plot like this to design the capsule. Depending on the level of pore blocking that I need, I can design what's the properties or what's the mechanical properties of the shell that I need in order to get the desired pore blocking. So we can use this in order to design our experiments. So the last part of this story is to try to see if these capsules actually displace oil. Okay, so we did that by looking at three-dimensional porous media using confocal microscopy to do this visualization. Following the pioneering work of our next speaker some time ago, where he used confocal microscopes to visualize three-dimensional porous media flow. So I won't go into the detail of confocal microscopy here, but the phases need to have exactly the same refractive index in order to be able to get the images. This is kind of like a tricky case that we need to play around to get the right viscosity level and refractive index level. We marked all the different phases with a different fluorescent dye. So what you're going to see here is the water phase is going to be marked in blue. The oil phase is going to be marked in yellow, and the capsules is going to be marked with this pink color. So we started in the initial state by having just a porous media almost fully saturated with oil. That's why you see all this yellowish color. There's water. Water is the wetting phase here. So there's some irreducible water saturation in the porous media, around 16%. We inject water. So water flows through the three-dimensional porous media, leaving a lot of trapped oil ganglia. So all these yellow areas are oil ganglia trapped by capillarity. And the remaining oil saturation in this case was around 33%. So we inject capsules, which are marked with this pink. So these pink spheres are the capsules. The capsule flow through the water path and start blocking the preferential water path. As it blocks the preferential water path, it diverts water to oil-containing pores, and then you can see after the injection of the capsules, the water the oil ganglia distribution changes, and then the residual oil saturation dropped to 26%. Just coming back here was 33%, and then we got to 26%. And here's an evidence of oil coming out of the porous media. So this amount of oil that was recovered after the injection of the microcapsules. So I'll jump this slide because of interest of time. So just to conclude this first story, we were able to produce microcapsules with different diameters and different mechanical properties. And then we proved that we can use them to do this pore blocking. There's still a lot of challenges in this research area. We need to actually be able to really specify what are the properties of the capsule that we need for the different situation in an oil reservoir. And more important, if we want to do that in a practical way, we need to develop a large-scale production of microcapsules. If we need to make 1 ton of these microcapsules, won't be by the microfluidics that are used in the lab. So the second quick story that I have here is looking at the surfactant alternate gas injection. This is the PhD thesis of Nicole Lima. She's finishing up her thesis. The idea is that if you inject both water or gas, you're going to get viscous fingering because of the low viscosity of both water and gas, and you can also have gravitational segregation. So if you're injecting gas can flow up towards the higher part of the reservoir, and water can flow down. But now if you have a surfactant solution, that you inject gas behind that, you will form a foam inside the reservoir. And as you form the foam, a foam has an apparent, much higher apparent viscosity. So you're gonna make this phase that's flowing and displacing oil act as a very high viscosity liquid. And as it has a very high viscosity liquid, would lead to a much uniform displacement front. And also you avoid this gravitational segregation, okay? So this is very old data that shows that the gas permeability with foam is much less than the gas permeability without foam. So you can really lower the permeability of the gas phase by having this foam. This is some visualization experiment done at Lisa Biswald's group at Rice, showing that when you form the foam, where the liquids, how you're able to displace in a more uniform way. So what Nicole is doing is trying, in this part of her thesis that I'm showing you here, is try to displace oil doing this alternate surfactant solution with gas. So we use a porous media microfluidic device that I'm showing here. We saturate this porous media with oil and then inject water and water with surfactant. So it's a surfactant solution. And then we inject gas behind that. So this is the end of the water injection process. I'll just show a movie here to highlight some of the important points. So water is this pink phase and oil is this brownish phase. You can see that the water displaced the oil. It left some oil ganglia that was trapped. At this point of the experiment, we are injecting water and getting water out of the microfluidic device. So the oil is trapped, is not moving anymore. So now we start injecting gas. I'll speed up this because this is a very long video. You can see that the gas is basically flowing through the water containing pores because it's easier to flow through the water containing pores. But that, as time goes by, this is a surfactant solution. So the gas is flowing, displacing this water and starting to form a foam. You can start seeing a bunch of lamellas being formed here. And these lamellas make the flow resistance through those paths much stronger. So now you're going to start displacing the oil containing pores. So as time goes by, just accelerating the experiments here, you see that you're going to see less and less of the brownish color. And you can see now a lot of foam. You see a lot of lamellas on this as the gas got mixed with the surfactant solution. So we can get what's the remaining oil saturation after the water phase injection and after we inject the gas phase. Okay, so if there's no surfactant, so this is basically a WAG. After you inject gas, there's very little gain. So the oil, the reduction of the oil saturation was around 3%. But when we inject a gas following a surfactant solution injection, you can see that there was a reduction in the oil saturation of around 14%. So it was a very appreciable reduction. This is the concentration of the surfactant in the water solution. This is way above the CMC of this surfactant solution. But if we increase this, so the concentration even more, the surface tension doesn't change anymore. We are above the surfactant of the CMC, but you form way more lamella in this higher concentration. As we form more lamella in the higher concentration, basically the foam has a stronger flow resistance, so you're able to displace even more oil. So as we change the concentration of the surfactant solution, you go to a reduction of the oil phase of around 21%. So this is showing the advantage that we get by forming the foam inside the porous media and using that foam as a mobility reduction agent. Here's the injection pressure, and we can clearly see that as we increase the concentration of the surfactant solution, the pressure peak gets higher and higher. And that's one of the reasons why you're able to displace more oil, because the flow resistance is getting stronger. So you get higher inlet pressure, and that basically helps you displace the oil phase. Okay, so as a final remarks here, we see that we are able to form these foams or lamellae by when the gas is displacing the surfactant solution. And then that changes the pressure distribution inside the pore space. And then that pressure distribution is able to displace the oil that was trapped by capillarity. So with that, I want to thank you for your attention. Again, I leave my email here in case you have any question. This is a somewhat old photo, but I want to thank who actually do the work, which is all these guys. And I highlighted here the ones that I discussed their research in this presentation. Want to thank also the funding for the porous media research in the labs. And then I'll be glad to answer any questions in the discussion session later this afternoon. Thank you very much.
So, Marcio, many thanks for your talk. Very nice group here. Outstanding presentation. So, in this fourth Brazil InterPore chapter meeting, we have a last section for question and answers for all the speakers. And now we move to the next speaker. So it's my pleasure to introduce Suji Datta from Princeton University. The word is yours. Be welcome.
Thank you. Let me share my screen.
Please.
And okay. Can you see this okay? And you can see
yes,
some stuff moving around on the...
Yes, very nice.
Okay, perfect. Well, let me just... Okay, good. Well, thank you all for being here. Thank you to the organizers for this kind of invitation, and also for just putting together such an incredible 2 days of workshop. It's really been just a really very inspiring set of talks. So thank you all. Obrigado. I hope to learn more Portuguese as time goes on. So my name is Suji Datta. I'm an assistant professor here at Princeton University in chemical and biological engineering. Marcio's talk beforehand was a perfect segue to what I will tell you about today. So thank you for that. Today I'll tell you about some of the work we've been doing in my lab over the past few years, studying viscoelastic polymer flooding in porous media. And so I'm sure this is a topic that many of you might be interested in. We've heard various people, especially this morning, talk about the importance of polymers in porous media. And so today I'll tell you about some of the work that we've been doing, trying to connect the pore scale features of the flow to macroscopic properties of the transport. And so first, I just wanted to give you a quick overview of the work that my group does before I tell you about this specific topic. So as Marcio very nicely mentioned in his talk, broadly speaking, my lab studies the dynamics of soft and living matter in complex and porous media. And there are three areas that we focus on in particular. One is this classic problem of better understanding how fluids flow through disordered 3D porous media, which you've all heard many talks on and which I'm sure you're all interested in. What we do in my lab is we make our own model 3D porous media that are completely transparent, and so we can visualize the flow inside of them using confocal microscopy. So this is just an example of a movie that we took showing oil, that's the black stuff, displacing water, that's the bright regions, from deep inside a 3D porous medium. And as you can see from this movie, the oil doesn't just flow smoothly from left to right, but it flows through this classic fingering pathway. And so by taking movies like this, we've been able to develop a deeper understanding of the underlying physics. And so in the past, I spent a lot of time studying these immiscible fluid displacements in uniformly disordered porous media. More recently, my lab has been studying the influence of structural heterogeneities, things like pore size gradients and layers of different permeability. And those heterogeneities completely change the flow behavior. And so we've been developing new principles describing immiscible fluid displacements in heterogeneous porous media. We've also been studying how colloidal particulates transport through porous media, how they can get stuck in various pores, similar to what Marcio told us about, how they can redirect the flow, how they can get pushed through by the flow behavior. So we've been visualizing those coupled dynamics. We've also been studying what happens when you have viscoelastic flows. That's what I'll tell you about today. And I'll just give you a quick teaser. This is a movie of a polymer solution flowing inside a porous medium. This is a movie just inside one pore showing you the flow. So that's shown here. And even though in all of these flows, the Reynolds numbers are always much less than 1. They're slow, viscous dominated flows. So typically they're laminar. They don't change in time. They're smooth. It turns out that in polymer solutions, because of the polymer elasticity, you can actually get chaotic flows that look like they're turbulent, even though the Reynolds numbers are always much smaller than 1. And today I'll tell you about some of the work we've been doing trying to understand how this chaotic flow due to polymer elasticity impacts the macroscopic flow behavior. We've also been studying what happens when you have swellable and shrinkable porous media, so they're deformable. Similar to what Marcio talked about in this previous talk, we've been studying porous microcapsules, how they buckle, how they change shape. More recently, my group has been studying what happens when you have poroelastic networks of multiple particles, and it turns out that they can actually self-heal in some surprising ways. We've also been studying what happens when you have swellable particles like hydrogels confined in porous media, and confinement also fundamentally changes their behavior. And then the third area that we focus on in my lab is we study living bacterial communities and how they move and sense chemicals and degrade contaminants and do all sorts of things in porous media. And so in particular, we've been studying the motility of bacteria in porous media and how they chemotax and grow and do all sorts of important processes. And so today I'll tell you about the work we've been doing studying polymer solutions in porous media. And all of the work that I'll tell you about was led by an incredible graduate student in my lab, Chris Brown. We did some earlier work where we studied the flow in microfabricated 1D pore arrays. We published that last year in JFM. Here's a reference here. I will not tell you about that work today. Instead, today I'll tell you about our more recent work where we've been studying the flow in full 3-dimensional porous media. And we put some of that work on the archive in this preprint a few months ago. Please feel free to check that out if you're interested. Also, please check out our lab website where we have links to all of these different references. And of course, we've benefited tremendously from interactions with our colleagues both here at Princeton and elsewhere, some of whom are listed here. And I look forward to interacting with many more of you in the future. And so I don't think I need to tell you all that this is an important problem. Polymer flows through porous media arise in many engineering applications, ranging from filtration and extrusion and chromatography to this classic processes of oil recovery. And we've heard this morning about how polymers are often used for conformance control. And we've also heard that Brazil in particular has tremendous oil resources that are waiting to be extracted, and using polymers is one way to do that. A similar problem arises in groundwater remediation, where you want to remove contaminants, immiscible contaminants trapped in groundwater aquifers, and polymeric formulations are often used for that. And more recently, inspired by some of the talks that I heard in this workshop today and yesterday, and a recent interest in geothermal energy, it may be that using polymers can help promote mixing and heat transfer in geothermal systems. And that's something that we're also very interested in. And so in all of these cases, the simplest question you can ask about whatever polymer solution you're using is, what's the relationship between the pressure drop across a given porous medium that you're injecting your polymer through and the flow rate? The volumetric flow rate is Q, divided by the cross-sectional area A. So this is the Darcy flux. What's the relationship between the pressure drop and the flow rate, right? This is the most basic descriptor of the flow that you can imagine. And so typically we use Darcy's law, right, shown here. And for a polymer solution, often what people do is they replace the shear viscosity that you typically use with what's known as the apparent viscosity, right? So this is the effective viscosity of the polymer solution inside the porous medium, right? So the apparent viscosity is how you quantify the macroscopic resistance to flow of a polymer solution through a porous medium, right? And even though people have been using polymer solutions for decades and decades and decades, we still don't know how to predict the apparent viscosity of a polymer solution inside a porous medium. This is the most basic description of the flow, and it's still a challenge to be able to predict this, right? And so what we set out to do in our research, and what I'll tell you about today, is we wanted to understand what determines the apparent viscosity of a polymer solution injected in a porous medium, and how can we predict it, right? And this is, of course, one of the most important things you need to be able to model the flow of polymer solutions in porous media in macroscopic scales, right? And so this brings us to this puzzle, which has been around for over 50 years. To my knowledge, the first studies were done by Marshall and Metzner in the 60s. And what they did later on, followed up by Chapoteau in the 80s. And what they did is very simple. They took polymer solutions. These are high molecular weight polymers, which are typically shear thinning, which means if you measure the viscosity, so look at the open circles here, the shear viscosity, in a shear rheometer, as you increase the shear rate, the viscosity typically goes down, right? They're shear thinning. And yet, what these people found is when you inject a polymer solution into a porous medium and at different flow rates, which corresponds to different shear rates, and measure the overall pressure drop, and then use Darcy's law to infer what the apparent viscosity is. So that's shown by the solid points. The apparent viscosity agrees with the shear viscosity until you get to a critical flow rate or a critical shear rate, at which point the apparent viscosity anomalously increases, right? The macroscopic flow resistance anomalously increases, sometimes very sharply, for a polymer solution only in a porous medium. In a porous medium, the flow resistance goes up, even though these polymer solutions are shear thinning. This is the puzzle, right? And the question is why? And so there have been many explanations proposed over the years, right? The original explanation was maybe, you know, as the polymer solutions move through these tight converging channels inside the pore space, the polymers get stretched out, which gives rise to some extensional viscosity. Maybe that's what's going on, right? But there's been no direct tests of that. Perhaps what could be going on is that the polymers are getting stretched out, and as they stretch out, they stick to the walls of the surrounding pore space. They clog the pores, reduce the permeability. Maybe that's what's going on, right? That gives rise to a larger pressure drop, right? In some cases, that is indeed the case. But as what I'll tell you about today, that's not necessary to explain this anomalous increase in the macroscopic flow resistance. More recently, there was a group at Schlumberger a few years back that proposed that maybe what's going on is these polymer solutions are highly elastic. And what happens is that as these elastic stresses build up in the flow, it takes some time to relax. As the elastic stresses build up, they actually give rise to flow instabilities, and they cause this chaotic flow that's often known as elastic turbulence, right? And they propose that maybe elastic turbulence arises and gives rise to this anomalous increase in the macroscopic flow resistance. But we don't know. And then even more recently, this possibility was kind of cast into doubt. There's this very nice paper in PRL last year where Jeff Guasso's group showed that in some cases, in 2D ordered porous media, when you introduce disorder, these flow fluctuations actually go away. And so it seems that disorder actually can suppress these chaotic fluctuations. So maybe elastic turbulence doesn't even arise in disordered porous media. Although even more recently, there have been some other papers showing that maybe this is not a general phenomenon. And so it's unclear, right? We don't know what's going on with polymer solutions inside porous media. We don't know why the apparent viscosity increases above a threshold flow rate. And so what I'm going to tell you about today, I'm just going to jump straight to the punchline. I'm going to show you that by directly visualizing the flow inside a disordered 3D porous medium, we were able to show that elastic turbulence does arise. The flows become chaotic due to the polymer elasticity. And we were able to show that by mapping out the flow behavior, these chaotic flow fluctuations give rise to increased viscous dissipation, which explains why the macroscopic flow resistance anomalously increases. And using these insights, we've actually been able to come up with quantitative guidelines for predicting what the apparent viscosity of a polymer solution is inside a porous medium. And so how do we do this? again, Marcio touched on this very nicely in his talk. We make our own model 3D porous media by taking borosilicate glass beads, packing them together in a quartz capillary, sintering them at just very briefly at 1000 degrees Celsius so that the beads fuse together and form a rigid porous medium that doesn't change shape, right? This is still opaque though, you can't see through it. So, and by the way, the beads that we use are around 300 micrometers in diameter. The porous media are typically tens of beads across and hundreds of beads along, right? But this is still opaque. We still can't see what's going on inside. And so what we do is we developed a trick where we formulate a fluid that has the exact same refractive index as the solid glass. And so when you infiltrate the pore space, everything becomes transparent and you can visualize everything in 3D using confocal microscopy. I promise you the porous medium is still here. This is the same porous medium, but now we filled it with one of these refractive index matched liquids. And so everything becomes transparent. You can see right through. And so by selectively dyeing the different components, we can visualize them in 3D using confocal microscopy. So for example, here we're taking slices throughout the porous medium. You can see these black circles are cuts through the solid matrix making up the porous medium. The bright is the pore space. And so by taking many of these slices, we can put them together and reconstruct the 3D structure of the pore space, right? So this is just one small field of view, but simultaneously, not only can we image the flow, so in our experiments, what I'll tell you about today, we seed the flow with tracer particles and we can visualize them and do particle image velocimetry to map out the flow behavior. But we can also measure the pressure drop across the porous medium. And so that way we can connect the pore scale flow to the macroscopic flow resistance. And so that's what we did. And so what polymer solution do we use? We use the typical polymer solution that's used in many field applications. We use a high molecular weight, partially hydrolyzed polyacrylamide in a viscous background solvent, right? And so this is a highly elastic fluid. The shear viscosity is constant. So this is the shear stress divided by the shear rate. The shear viscosity is nearly constant. Overall shear rates, right? So this is basically a constant viscosity fluid, but it's highly elastic. We can measure the first normal stress difference, which is a measure of how elastic it is, and we can characterize elasticity this way. And we can define what's called the Weisenberg number, which using the first normal stress difference and the shear stress, and the Weisenberg number essentially quantifies how elastic this fluid is and how important elastic stresses are in the flow. And so the first thing we can do is just do this typical experiment where we measure the pressure drop across the porous medium as we inject the polymer solution at different flow rates. So what I'm showing you here on the x-axis is the characteristic interstitial shear rate corresponding to each flow rate, right? So it's given by the flow rate per unit area divided by this characteristic pore length scale given by the permeability and the porosity, right? And we measure the pressure drop across the medium at each flow rate. And at low flow rates, it agrees with Darcy's law, just using the measured shear viscosity. But above a critical flow rate or a critical shear rate, we again see this anomalous increase, this deviation in the anomalous flow resistance, right? This is similar to what other people have published, but now we can actually watch what's going on inside the flow. And so here's one example of a pore. These black regions are the beads making up the pore space, making up the solid matrix. So here we've picked a pore that looks very symmetric. Typically, they're all very disordered. At low flow rates, we can see below this deviation, the flow is stable, it's laminar, it's unchanging in time. Above this deviation, we see indeed that the flow becomes highly unstable. It changes spatially and temporally, it's constantly fluctuating, even though inertia doesn't play a role in these flows, right? This is the hallmark of an elastic flow instability driven by polymer elasticity, right? And so the first question is, what's going on right at this transition, right? Between this stable flow and this highly unstable chaotic flow. And what we saw there is, in fact, we see these bursts of instability, right? So what I'm showing you here in purple is the background laminar stable flow field, and purple and blue and green and yellow show you bursts of increasingly unstable flow. So here we've subtracted off the background and we're just looking at the flow fluctuations. Right at that transition, we see these intermittent bursts of unstable flow. And then when we go to even higher flow rates, we see that these bursts are sustained over time and the flow is unstable over the entire imaging period, right? So it looks like we have a transition between a completely stable flow state and a completely unstable, chaotic flow state, right? And so here's an example of another movie where we're really looking with high resolution, and you can see the flow is highly chaotic. It's changing in time. You can see these little swirls and vortices that form and move around and grow and die away, right? This is an example of turbulence, but it's elastic turbulence. It's turbulence driven by the polymer elasticity, and it actually happens inside these porous media. We can see it. And we can characterize it using PIV. One important feature is that by characterizing the flow, we can ask, are there characteristic length scales or time scales in these flows, or are they purely chaotic? And when we characterize the flow, we see that the power spectral density of the flow fluctuations decays as a power law, both in frequency and in space. What that tells us is that these flows are chaotic. There are no characteristic length or time scales. And what's interesting is the majority of the power that's measured in these flow fluctuations is much longer than the polymer relaxation time. What that means is these fluctuations are slow. They're continually growing and shrinking, and they're slow over large time scales, much longer than the polymer relaxation time. And so how do we characterize this transition from this stable flow state to this unstable flow state? Well, what we can do is we can measure how long do these unstable bursts persist for? What fraction of time is the flow unstable? So if it's 0, that means the flow is completely stable. If it's 1, that means the flow is completely chaotic or unstable. And in between, that means some fraction of the time the flow is unstable. And we can measure that at different Weisenberg numbers, which I told you is a measure of how important elasticity is in the flow. And so here's what we see. When we look at many different pores, randomly scattered throughout the porous medium, right? Each pore at low flow rates or low Weisenberg numbers is stable. At a critical Weisenberg number or a critical flow rate, it becomes more and more unstable until it's completely chaotic, right? And the different pores become unstable, become chaotic at different critical Weisenberg numbers. Here's the distribution of the measured critical Weisenberg numbers. And so the different pores are different. They become unstable at different flow rates and different Weisenberg numbers. But when we rescale all the data by that critical value, all of these measurements collapse on top of themselves. What that means is, even though different pores become unstable at different flow conditions, they all show the same transition to this chaotic flow state, which is really interesting. And what this means is, at different flow rates, different fractions of pores are chaotic, are unstable. So for example, here are just 3 example pores. At a low flow rate or a low Weisenberg number, they're all stable, right? That's purple. And then as you increase flow rate, this one becomes chaotic and unstable. These 2 remain stable. And then at a higher flow rate, this one also becomes unstable. And at an even higher flow rate, this one now becomes unstable, right? And so we call this porous individualism. The different pores become unstable at different flow rates. So who cares? At the end of the day, what does this have to do with this macroscopic flow resistance, right? I told you at the beginning, we want to connect these pore scale features of the flow to the overall deviation, the overall anomalous increase in the macroscopic flow resistance. So what we did, so here are the pressure drop measurements plotted another way. This is the apparent viscosity divided by the shear viscosity. So at low flow rates or low Weisenberg numbers, it's just given by the shear rheology. Above a critical value, we see this anomalous increase in the apparent viscosity. And we want to be able to capture these data by understanding what's going on at the pore scale. And so I told you that at the pore scale, the flows are becoming chaotic. So we said, okay, let's try to calculate how much energy is being dissipated due to these chaotic flow fluctuations. And so I'll skip over the details, but we can do a very standard power balance of this flow where we balance the pressure work with the viscous dissipation. And by integrating over the entire volume and assuming that we have slow fluctuations, which we see in the experiments, and assuming that the accumulated strain by the polymers is not very large, and we've supported that with direct measurements, then we can turn this power balance into a very simple relationship where we can actually capture the macroscopic apparent viscosity, and we can split it up into two components. One is your standard Darcy's law using the shear viscosity, right? So this is what you typically measure in stable flows, with an additional piece that reflects the additional viscous dissipation due to these chaotic flow fluctuations generated by polymer elasticity. And we can measure those because we can do PIV of the flow, right? We can measure the velocity field, quantify the velocity fluctuations, calculate what the strain rate tensor is, and calculate the viscous dissipation that results. And so, long story short, here are the data. If what I'm telling you is correct, then we should be able to capture these pressure drop measurements, right, using our pore scale imaging. And so we took our pore scale imaging, we measured this viscous dissipation, we know all the other parameters here, and here's what we get. No fitting parameters. This is directly from the pore scale measurements. And what we find is that we can capture very nicely this anomalous increase in the macroscopic flow resistance. And what's more, I told you about how different pores become chaotic at different flow rates or different Weisenberg numbers, right? The shape of this distribution actually controls the shape of this overall measured flow resistance. This starting point where you start to see this deviation is when the first pores become unstable. As you increase in flow rate, more and more pores become unstable, the apparent viscosity increases, and then all of the pores are now unstable. And that's where this now saturates and eventually goes back down as the background viscous dissipation takes over. So at the end of the day, we measured this in the lab. We can show this in the lab. Does this matter in the field? And so we can do some back of the envelope calculations now that we have these new insights. For the characteristic pore sizes that you typically encounter in the field, the typical flow speeds, shear rates, and polymer relaxation times. These are high molecular weight polymers that can have very long relaxation times. The typical Weisenberg numbers that you might experience in the field are up to 10 to the 4. We saw that these chaotic flow fluctuations arise at Weisenberg numbers between 2 and 7, right? So while other effects like breaking the polymers and absorbing to the solid matrix can also arise, we do expect that these flow instabilities will be important in the field. And so with that, I'm going to wrap up by just summarizing what I've shown you today is by directly visualizing the flow inside 3D porous medium, we have been able to directly demonstrate that this elastic turbulence arises inside the porous medium in polymer solutions, right? We've been able to characterize how different pores transition to this chaotic turbulent state. And we found that the differences between the pores controls the shape of this transition. And by directly visualizing the pore scale flow, we were able to show how those chaotic flow fluctuations give rise to this macroscopic increase in the flow resistance. And so there are many more questions that we're now investigating, right? What determines those critical Weisenberg numbers? What's the impact of pore structure and fluid rheology? And I'm just going to end by connecting to what Marcio very nicely talked about in the previous talk. Many of you are interested in oil recovery, right? In using these polymer solutions to push trapped oil blobs out from a porous medium. And in fact, 10 years ago, there were reports from the Daqing oil field in China that when you use high molecular weight polymers, so not the conventional ones that you use in polymer flooding just for conformance control, but when you use high molecular weight polymers, like the ones I told you about today, these field tests in Daqing showed you that you can get more than 20% more recovery of the oil. And this has been a puzzle. Why is this the case? And what we think is going on is that this elastic turbulence is helping to push these oil blobs out. And so now what we're trying to do is we're trying to visualize individual oil ganglia trapped inside these 3D porous media and watch what happens when the flow becomes turbulent and whether or not it pushes the oil blobs out. So with that, we're trying to connect what we've learned to this bigger problem of oil recovery and in other cases, groundwater remediation. So with that, I'm going to conclude here. This is my amazing lab who make this work possible. This is my lab website. Please check it out. If you're interested in finding out more, send me an email if you have any questions. We're also on Twitter. Thank you all for listening. And thank you once again to the organizers for the invitation.
So many thanks, Professor Sujidata, for your very impressive talk on viscoelastic polymer flooding in 3D porous media. As you mentioned in your abstract, along with very interesting guidelines for predicting and controlling polymeric solution flows. Really very nice talk. Many thanks.
Thank you.
So I'd like to Márcio Murad, do you hear?
Yes, Gabriel.
Okay. Can you please continue as a chair?
Yeah, sure.
Okay.
Okay. Just a second, because I thought you were gonna. I think Alexei was the other chair.
No. It's not Alexei. I will present Aurora and then you continue, right?
Okay.
Okay.
Great. Okay.
Okay. Many thanks. So it's my pleasure to introduce Professor Aurora Perez from PUC Rio de Janeiro. Many thanks for your to accept our invitation. She will deliver the talk Formation and Stabilization of CO2 in brine foams from bulk to porous media. Please.
Thank you. Let me see if I can share the screen.
Yes, it's fine. Please go ahead.
Okay, thank you. Well, good afternoon and for everyone. It is a great pleasure to give this talk today. I have to say that I was thrilled when Grigory asked me to come and deliver a talk in this InterPore conference, and thrilled, not almost as terrified, because I am basically a chemist and trying to do some things related to porous media. So I'm very happy to be here. I have learned a lot with many talks, and I hope I can contribute at least with a bit of our late work on the formation and stabilization of foams related to porous media. Then I work in the chemistry department at the Catholic University in Rio de Janeiro, and I'm also the coordinator of the lab for studying surfactants, in particular the physical chemistry of surfactants. So we work a lot with soap and everything related to formation of micellar solutions. So just to tell you a little bit about our lab research, we have a lot of collaboration with the industry. So I hope this can be also a good motivation for the young students. You can see that we have our basic work is with colloidal dispersions, but we have work from nanofluids for EOR, going through formation and destabilization as well of heavy oil emulsions, and as well with quantification, characterization of polymers, such as the one just mentioned in the talk before, polyacrylamide, in produced water, in all these cases, you can see surfactants, polymers, nanoparticles are all involved. So that's what I talk about colloidal dispersions, but also all related to the oil industry, and all these projects have also funding from different industrial partners. And the other project that is our major project in the lab, that is the one I'm going to refer today, is that related to the formation of development of CO2 foaming formulations for mobility control in both enhanced oil recovery and carbon capture strategies. And it's a project that we have a very strong and fruitful partnership with both Shell here in Brazil and also Petrobras here in Rio. Then just to give you a context of this project is related to the scenario of the pre-salt in Brazil, in particular the challenges related to the high salinity found in these reservoirs and the high pressure also that is present. Another problem is the large amounts of associated gas, in particular CO2 in high amounts, that is produced from these wells. And this requires more complex gas processing technologies, as well as it can become an environmental problem, because the gas that is produced cannot be burned, cannot be simply released to the environment because of this great amount of CO2. And in that case, as was mentioned before, and several talks, there is this option of water alternating gas methods, which is a miscible gas enhanced oil recovery method. So this method, which is already being thought and applied and giving results, it has another challenge in its application, which is that the pre-salt reservoirs are constituted by heterogeneous carbonates as the rock. And these carbonates, they have variable reservoir quality in terms of a very variable porosity and permeability. And so this is just some pictures from the course that we got for our work in the lab, and you can see how this is analogous rock. Of course, this is not reservoir rock, but in this case, you can see the pore distribution and the permeability, how different can be in different sections of this rock. So this extra challenge present in the pre-salt reservoirs is responsible for many of the drawbacks that can appear in these WAG methods. And they are related, as Marcio mentioned also before, to the viscous fingering, gravity segregation effects, and especially channeling effects, which is this early gas breakthrough when it goes through these preferential channels. And in that context is then when appears this the proposal of this method, foam-assisted water alternating gas, which is also a method already known and used in several places since some years ago. And this is a hybrid EOR method because it combines the miscible gas principle with the use of chemicals to form this foam, which is going to be the major fluid, the important fluid here to achieve a more homogeneous displacement. So we have several advantages over the WAG method. It's possible to obtain an improved super efficiency, reduction of this gravity segregation, and delay this gas breakthrough. So these are things that have been also mentioned in many of the other talks. I just wanted to contextualize them when we got in our lab with the task of developing these foaming formulations and applying them to these challenges in pre-salt. So that's what I actually wanted to mention to start it here after contextualization in the talk with talking about foams. Foams are very interesting systems, but they are also very tricky systems, very, very difficult to work with. And that's what I like it very much. And I try to transmit that enthusiasm to everyone in my group when they are really going crazy with the foam behavior. So foams are arrays of gas bubbles that are dispersed in liquid or a solid phase. And in this type of array, then we can highlight the presence of these lamella or interfacial films, that is, in this case, a liquid foam. So it's a liquid film between adjacent bubbles. I'm not going to talk too much about the structure of foams because that would be the subject, could be the subject of another talk. But just in our identification of foams in day-to-day life, we are very used to talk about foams in healthcare applications, in food applications, and also in the case of when it's solid phase, we have other types of applications where the foams also are everywhere, actually. And in this talk, they're related here mostly to the foams that are formed with the liquid phase, also known as liquid foams. And in that case, I want to use also here, I want you to note that these liquid foams have some special characteristics that are common for all of them. First, you can see there is a varied texture of the foam. So that means they contain different amounts of gas. The foam phase is always on top. So foam is a fluid with a lower density than the liquid that is one of the phases. And they are predominantly white, and that's regardless, as you can see here, of the original liquid phase. And that's because they are colloidal in nature. And they also have a reduced mobility. So you can see some of the foams can be quite viscous, and they have quite reduced mobility. And that has to do with the entrapment of the gas bubbles and the amount of gas that is distributed inside those foams. And these characteristics that you can see in everyday foams are the ones that makes them very attractive for the using to reduce the gas mobility in these reservoirs. So let's talk about foam formation. Foam formation actually is quite easy. You just have to blow some air into a liquid containing foaming components. And it works the same for foams in bulk as for confined foams. And then bulk foams here, we mentioned they are these columns of foam that is formed as a 3D bubble array. This is how we can see this structure. And one of the characteristics is that the bubble size is smaller than the dimensions of this vessel that it contains. On the other hand, we have the confined foams that are the ones more interesting for this conference, which will be in that case, when the bubble size is equal or larger than the channel dimensions. In that case, we don't refer anymore to a bubble array. We talk of a bubble train or train of bubbles. And it's more seen as a 2D structure. And in both of these kind of forms, even when it's easy to form, keeping the foam is more difficult. And that's because foams are inherently unstable from the thermodynamic point of view. You have a dispersion of one phase in the other. So the tendency, the trend will be to decrease the total interfacial area. So it tends to collapse all these bubbles into one, as happens with emulsions and other dispersions. And then the main challenge with foams is actually that, obtaining certain stability, and that is even more difficult when you have extreme conditions, like in a reservoir, when you have high salinity and high pressure. In terms of the destruction mechanisms that lead to this decreased stability in foams, we can mention the mechanism of gravitational drainage that also has to do with the segregation and the bursting of these bubbles once they reach the top part of the recipient. And then you can see that capillary suction can also be included into this destruction mechanism for foams when you have a flow, preferential flow of liquid, depending on or driven by the difference in pressure inside these channels. Then it all goes to the coalescence of the droplets into the reduction of this interfacial area. And a characteristic of mechanism of these dispersions is the gas diffusion. In this case, that we have a dispersion of a gas, also known as ripening or coarsening phenomenon, which is when you have the migration of the content inside the bubble from the ones that have a smaller radii to the larger radii because of the difference in pressure. And this kind of mechanism is particularly important when you're using CO2 as a gas, because the diffusion of the gas is directly related to the Henry constant and is directly related to the solubility of that gas in the water phase. And just for comparison, we can see that that constant for something like nitrogen or hexafluoride gas, it goes to 0.01, 0.001, so it's very small, so it's much less soluble. The diffusion is much slower, but you see that for CO2, it has a much higher value, and that means that the CO2 foams experiment a lot of osmolar ripening, and that's the major cause of destabilization in this type of foams. Then how do we arrest this mechanism? Well, we stabilize with materials and molecules that are active at surfaces like surfactants, polymers, and nanoparticles. They are the main component of these foam formulations, and they act decreasing interfacial tension, which makes more homogeneous the droplet distribution. And they increase surface elasticity, which is the major stabilization mechanism for these foams due to the Gibbs-Marangoni effect, increasing the disjoining pressure, especially when you have ionic, you have charges in these materials, and then you can have electrostatic effects, or in the case of polymers and some nanoparticles, static effects as well, and increasing the viscosity of the liquid phase because it can reduce the dryness and capillary suction. And then while this first effect here is more important for the bulk foam, the increased viscosity of the liquid phase is more important for the liquid foam. Then you have a decrease in interfacial tension and also in surface elasticity condition pressure, affecting as well the foams in porous media as well as in the bulk phase. So how to select a suitable foaming formulation for CO2 foam? If we look at bulk foams, we need to look at the ability to generate the foam cone and the ability to the foaming formulation be able to prevent or reduce the foam destruction. And these are kind of static indicators. We have a foam that is formed, and then we just observe with time how it develops. But when we have these confined foams in porous, then we have more dynamic processes. Now foamability is related to the ability to generate that lamella, while the stability can be measured as the ability of the surfactant to prevent and reduce the lamella destruction and to regenerate, which is a big difference with the bulk foams, the lamella after breakage. So we have to look at different phenomena, even when the basics of formation and destruction of foams are the same in both cases. And in the case of bulk foams, when we work with them, they actually represent a fast and simple screening methodology for formulations, because it allows to identify the main destruction mechanisms for specific compositions, but they don't give realistic flow behavior when you talk about confined space like in reservoirs. In the case of these dynamic processes, then we can achieve resemblance of the reservoir conditions in terms of the type of behavior, the type of flow, but it's more complex and experiments, and they take longer time. So they have both advantages and disadvantages. And then I just wanted to show you some examples that we have done in the lab using both approaches to study this formulation for CO2 foams. I'm gonna talk here about only one surfactant. We have screened more than 50 surfactants in our labs. In this case, it's ionic surfactant that is stable in injection brine, and we use it at a relatively low concentration. It's 0.5% weight, which is okay for the foaming because it's above its CMC. And we also have used some silica nanoparticles at very low concentration just to also be able to recognize the different mechanisms. So we first do this bottle testing screening to see which formulations foam more or less, to do that, to select the appropriate conditions. And then we go into more complex experiments. So for example, here we have the behavior of bulk foam, CO2 in brine, injection brine, using the surfactant, as I say, at 60 degrees Celsius. And you can see here that when we go from 50 bar of pressure to 100 bar of pressure, even when it is bulk foam, it has a huge impact in the stability of the foam. You can see here that for the higher pressure, when you can see the foam is more rapidly stabilized, and this has to do because with the increase in solubility because of becoming supercritical in this case at that pressure. Then as pressure goes up, we can also compare, for example, nitrogen foams with the CO2 and the supercritical CO2. So you can see here that the foams formed with nitrogen at 100 bar, they keep this narrow bubble size distribution, and it has a much longer stability. When you go to the CO2 at 50 bar below supercritical conditions, they are less stable already than the nitrogen foam at 100 bars, but they are more stable than the supercritical foam, as you can see here, which is rapidly destroyed, mainly because of bubble quartzoning. You can see even in this one that gives you more time to observe the 50 bar. The bubble size is increasing as the time goes by, and the nitrogen now is starting to get some larger bubbles, but it's still nothing compared to the speed of the foams with CO2. And when we add nanoparticles, then we can, as mentioned before, get this electrostatic and steric propulsion that we expect decrease the CO2 diffusion and increase the film resistance, in this case of the lamellas. And you can see here that when we do the same kind of experiment, looking at foam stability, when we have nanoparticles, the formulation is able to increase the foam half-life by 4 times, and then go from something about less than 1,000 seconds to something about 1 hour here for that half-life. So even a very small amount of nanoparticle is able to arrest here the quartzoning of the CO2. And then we tried, we had a very nice collaboration with Professor Mehran Sorabi and his group at the Harvard University to look at some of these foams in a micromodel rig that also we were able to do it at 100 bar of pressure and 60 degrees using the same surfactant and 50% of foam quality in fractional gas. And then the micromodel has this characteristic. There are many details that we recently published a paper with this work. So I encourage you, if you're interested in looking at the details in this paper of how we did the experiment. But as you can see, it's a glass micromodel with varied pore pattern. And then going directly into the stability of the foam now, this CO2 foam in the pore network, you can see that while using only surfactant, we obtain very few, very thin lamella through the micromodel. Then when we add the silica nanoparticle, we have the silica nanoparticle into this foam, stabilizing the foam, then we can have a larger amount of lamella. And the other thing is when we mix the CO2 with nitrogen, so we have this mixed gas, we decrease the solubility of the gas inside the bubbles, then we have a larger amount of lamella, and also we have this higher density in different zones, and it's easier to visualize different effects. The lamella is thicker than compared in both cases with the surfactants. And also here you can see the bubbles are more rounded than here when you have a more dry foam. So we went to try to understand the different mechanisms that can lead to this. And you can see that we compare what we obtain in the micro model in terms of a structure with the pressure drop for the different systems. And while for the, in this case, this yellow, kind of yellow here is the surfactant, this is the value for the pressure drop. You can see there was an increase, a significant increase when we used the nanoparticles, but the introduction of this nitrogen gas in the mixture for the gas phase, then is able to have a sudden increase here in the pressure drop. So this increase in pressure drop, what we I correlated, what it means is a resistance to flow inside the macro model. So we have a control, a mobility control when we reduce this mobility, as Marcia explained also before, that is important for the displacement of oil. And then here is our was our kind of interpretation of these factors. And we have the three systems. You can see here now in numbers the great increase here when you introduce nitrogen, but also there is a certain increase here of the pressure when we use nanoparticles. But what is more astounding is the increase in the number of lamella. So even when in the figure before that I showed the micro models, you saw that the lamella were similar, increase in both cases, both with nanoparticles and with the nitrogen. But the difference here is much larger in terms of number of lamella that we were detected, and they are both much higher than that obtained just with the surfactant. So this is very important because we can see how the very small amount of nanoparticles which are not large, the concentration is not high enough as for to raise the worries about blocking the pore throats or the pore channels, is able to increase this pressure drop. And on the other hand, a more realistic scenario is not just injecting CO2 into the reservoir. It's actually injecting this gas mixture that comes. In this case, we use nitrogen to simulate, to use as an equivalent for methane, which is the gas that is used in this mixture. So we wanted to see, well, what happens? This is like the worst case scenario we're going to have. The real scenario is going to be this one here. And you can see that there was a great increase here and a great formation, increase in density of lamella. The micromodel experiments also allowed us to visualize some of these foam generation and regeneration mechanisms of this confined foam that we weren't able to see, of course, in these bulk foams. And these are more important and more relevant for the application for EOR and carbon capture. And you can see different mechanisms like a snapshot of lamella division, leave behind. You see here, we have, for example, some of these bubbles. You can see here how they are divided in two of them. So there were a lot of details that we were able to see here. And it also allows us to confirm the importance of the Oswald ripening effect and compare for the different cases, which is the main mechanism affecting the CO2 foams. And in this case, for example, when we have the mixture of CO2 and nitrogen, we can see, for example, if we follow one of the bubbles, like this one is bubble 3, you can see that the size is being increased, while the size of this bubble 4 is being decreased, which are adjacent bubbles in this bubble train in the channel. So we can do a follow-up of this Oswald ripening effect. And we have done also some work on that, getting some graphics and some trends. So as the important lessons learned for us in this very initial work, we're going into the porous media. We work more with foams in bulk than these confined foams. We're happy to say that it was possible to obtain kind of a stable, like metastable CO2 in brine foams that were able to migrate through a porous media and reach a certain pressure difference. The bulk foam experiments were essential for rapid screening and formulation, even emphasizing the importance of using high pressure for these experiments to have an actual result, and to identify the main destruction mechanisms for the target foam, in this case, both CO2 and nitrogen used as gas. These micromodel experiments also allow to visualize the formation and the texture of the foam in these porous media, how the different strategies we use to achieve stabilization can influence in this gas mobility control. And as a plus, we were able also to assess if possible nanoparticle aggregation will block these pore throats. So for nanoparticle uses, it's essential to use microfluidic experiments, because it's something you cannot infer from the bulk foam experiments. And in terms of open challenges, we have many in our labs, and these ones here that I pointed out because I regularly mentioned it, that I can throw some of these challenges to the whole community. If you want, we're open for collaborations. We need to do more studying on the time scale of this stabilization mechanism in the porous media. Time-related experiments are very important. There is an important factor, which is the fluid-solid interactions. In this case, will be bubble-solid interactions, and we have it needs to be looked into the effect of rock composition and wetchability in the case of carbonates, in particular, that are very reactive rock. Interfacial viscosity versus bulk viscosity is important to separate and see how each effect can influence the stability of these confined foams in these porous networks, and to model the parameters to take into account those while ripening in foams containing CO2 will be, we believe, an important addition to the simulation of these foams. And we believe that understanding the physical chemistry and the mechanism behind that, making use both of bulk and micro and confined foams, are very important for this modeling. And finally, I just want to acknowledge all my team at GlassSurf and Tuki Rio, which is a very enthusiastic team and very multidisciplinary. We have from electrical engineers and mechanical engineers, petroleum engineers, chemical engineers, and pure chemists working all together here. And we need all that to be able to understand a multidisciplinary problem that it is the making of these foams and the study of this foam behavior for these applications. And in particular, I want to mention Dr. Leandro Lopez and Juliana Fassagna for this work presented here. I want also to acknowledge the great collaborations that we have with the industry, Shell Brazil and Petrobras, and it's not only for funding, but we also have a lot of input from the scientific point of view in these discussions. So they feel that our research is relevant for their work, and we also feel they are interested in following our knowledge, basic knowledge in these applications. And of course, the support from the university and the chemistry department. I also want to thank the group at Herbert Watt and Grigory's group here in Juiz de Fora, which is also helping us a lot in this understanding and modeling. And finally, the InterPore organizing committee for the invitation. And thank you all for listening to the presentation.
Okay, Professor Aurora, it's very nice talk, very impressive. So as we said, the questions will be posed in the discussion section. And now we're going to move to the last speaker of the section, Professor Fabiano Wolf. Mm-hmm. Is he there? Is he there?
Yes, I'm here.
Okay. I didn't see your answer. Yeah.
Okay, just a second.
Okay. He's from the Federal University of Santa Catarina at the city of Joinville. So, Professor Fabiano, the floor is yours. Go ahead.
Okay, thank you. Just a sec. Let me put here. can you see my presentation, Professor?
Yes, yes.
Yes. Okay. Okay. First of all, I would like to thank Professor Márcio Carvalho and the organizers for inviting me and presenting a little bit what we have been doing at UFSC Joinville. So it's a pleasure for me, it's an honor for me to be here today. So the title of my work is Creation of Dual Porosity Micromodules for Carbonate Rocks. This work had collaboration of Professor Diogo Siebert, Professor Marcelo Carreño from USP, the doctoral student Alexandre Lopes from USP, and Rodrigo Surmas from SEMPS Petrobras. The motivation of our work is related to a conversion technique used by the oil industry based on injection of water in a reservoir rock. The method is called water fluiding process. So the water fluiding process has the intention to keep the pressure on the system and keep the production. But sometimes the displacement, the injection process cannot be so efficient. So since some preferential fluid flow can happen in the system. So in this case, to understand better the reasons of that behavior, sometimes it's important to understand, to see that fluid flow from a microscopic point of view. So our intention here is to show a way to analyze the single phase and two phase flow under a microscopic view, considering the Porous scale. In this study, we have considering some carbonate rocks. Carbonate rocks are very complex structures when you look at the internal regime. Say that kind of rock can present a very wide pore size distribution. So it's possible to see pores and with a size of millimeters, and we can see in the same sample pores with some micrometers. So most of times you can relate the porosity with some macro scale part called microporosity, and you can consider the other part of porosity associated to the microchannels, or we can say a microporosity regime. So the scale threshold for this scale is not so well defined, but you can see here that pores less than 10 micrometers, so equivalent, can be considered in the microporosity regime. When you analyze some carbonate rocks, you can, it's possible to recognize some important types of microporosity in these systems. Cantrell and Hargert have classified 4 types of microporosity. Microporosity associated to the grains, some microporosity associated to the matrix, some microporosity associated to the equant cement, and microporosity associated to fibrous to blade cement. So there are 4 important types that can be analyzed and can be seen when you are looking to understand some physical mechanisms occurring at Porous scale. In this work, we have considered some has a good starting point, some Arab carbonates. Arab carbonates have some interesting characteristics. For example, Cantrell has observed that microporous grains are common and constitute the most volumetrically significant microporosity type. Independent on the microporosity forming process, he has observed that all the grain types have similar internal microstructure. He observed too that microporosity consists of a network of highly interconnected uniform size pore throats that intersect with some equant pores. Some scanning electronic microscope examination of pore structures shows that the pore geometry of microporous matrix is really similar to that observed for microporous grains. In order to analyze, to study the physical mechanisms occurring at pore scale, we have considered a micromodule approach for this problem. Micromodules are simplified and idealized porous media that can be used to analyze several mechanisms occurring at pore scale, as oil trapping and oil mobilization. There are different approaches for creating, for fabricate some a macromodule. You can use some approach based on regular structures. You can use approach based on some kind of mesh, like Delanoy or Voronoi tessellations. You can use some thin sections of rocks. So there are other approaches for the problem, but generally you can see the micromodules in one of these categories. In our case, we have realized that there is no so many works talking about two or more scales microstructures. So we have, thinking about carbonate rocks, we have proposed a methodology to create a dual scale micromodule using a Voronoi tessellation method and including some information from experimental data. For example, we can consider some mercury intrusion porosimetry in the creating process. It extends the work introduced by you in 2012. As we can see, you can create different models of distribution of macro and micro porosity considering this kind of approach. Voronoi tessellation is a method based on a set of points randomly distributed on a square domain, and you can create some polygons associated to those points. So that polygons will turn can be seen how has grains, solid grains in the final structure. So each polygon associated to each point on the domain can have its edge converted in a transformed or converted in a channel. So you can create using this approach some kind of porous structure in which the channels represent the edge represent the channels of the system, and the polygons represent the grains associated to the medium, to the porous medium. To extend a little bit the work by Wu, we have considered a pore size distribution extracted from some mercury intrusion porosimetry. We have analyzed that data, and you can see you have analyzed that. You can see that there are two scales well defined, and you have adjusted some Gaussian curves to each scale. So combining that Gaussian curves, you can have a combined function that can be adjusted to the data, and you can create from that a micromodel with this kind of information. Unfortunately, we have some manufacturer limitations when are creating micromodules. At that moment, the facilities available at UFSC have a minimal width channel to allow us to create a minimal width channel of around 10 micrometers. In the same way, it's not possible to create so big micromodules. So we had the limitation of a maximum ROI, a maximum regime of interest area of around 25 times 25 square millimeters. Using based on these manufacturing limitations, we could create a micro scale related to channels with 150 micrometers and a micro structure based on channels of around 15 micrometers. To create a two-scale micromodule or a dual porosity micromodule, you can combine these scales, these two images according to a specific way to produce a specific dual scale structure. Here you can see some structures performed to analyze the micromodels, the two-scale micromodels. You can see here one case that is very important, that can consider some microporous grains in the system. It's a very important type of microporosity that can be analyzed, that can be investigated by this kind of study. We have considered some micromodules with microporous grains, and a fraction of that macro scale channels converted into microporous matrix. And the last one considers a more heterogeneous cases, a case that in which we have some big cavities or vugs in the system, and all that initially micro scale channels filled by some microporous matrix. So in this case, the pores, the vugs have around 100 times, are 100 times larger than the microchannels. So you have really a more heterogeneous case in this situation. The process used for us to create the micromodels was based on photolithography. It was the micromodels were created in the microelectronic laboratory of USP by Professor Carreño and Alexandre Lopes. The process, the photolithography, is there presents a lot of steps. So here, in fact, it's not possible to detail all the steps used, but I can send you any reference about this subject if you want. Here you have a dual porosity micromodule, considering in this case some microporous grains, and so an important type of microporous microstructure, dual scale microstructure. In this, after creating the micromodels, we have analyzed some properties. We have characterized them. So for that, we have used the following experimental setup. which is based on a syringe pump, a stereo microscope with transmitted light, a flow-through pressure sensor, a bottle of CO2, and some more accessories used commonly in microfluidics lab. So this setup can be found in most of microfluidic labs. So it's in fact a simple structure, a simple setup. Here we have some results obtained from our analysis. To characterize the micromodel in terms of porosity, we have saturated the micromodel with diet water. Before that, we inject some CO2 in the system to displace air. This process makes easier the elimination of bubbles in the system. After that, you have taken 4 images using the digital camera coupled to the microscope, so that those 4 images was after that mounted using ImageJ plugin called Tracking2, and the porosity was calculated by binarizing the micromodels using ImageJ, and the porosity is based on the fraction of black pixels on the image. So here you have some comparison with between the original digital image used to fabricate the micromodels and the experimental counterpart calculation. So the errors found here are smaller than 7%, as you can see. After that, you have performed some permeability measurements. For that purpose, we have considered Darcy's law. Darcy's law relates the volumetric flow rate with the pressure drop across the system. Here, the permeability is a constant proportionality constant between the flow rate and the pressure drop. So here we have the cross-sectional area represented by A. The L is the micromodel length, M is the viscosity. As you can see here, the relationship between the pressure drop and the flow rate is linear shaped, so in good agreement with with Darcy's law. So as you can see, the results can be, as you can see, the results, the permeability can be calculated by using a linear regression based on the data obtained on the experiment. Here we have some results for permeability. It's possible to see that permeability, the presence of grains in the system, the microporous grains in the system, increases the permeability in that significant way, in fact. On the other hand, if you have microporosity in the microchannels, or thinking like a mud, a microporous matrix in the system filling the big channels, you'll see the permeability, in this case, the permeability go down. So depending on the position of the permeability of the microporous region, you can see it can influence in different ways the permeability of the system. For comparison, we have performed some numerical simulations using the LBM. So to analyze the trend of the experimental, to verify the experimental tendency according to the presence of the microporosity on the system. So we have As you can see, it's possible to see a good agreement between numerical and experimental results. After that, we have performed some two-phase flow analysis. You have performed a drainage process considering fluorinate oil, FC32H3, provided by 3M. In this circumstance, the oil is a no wetting fluid for the PDMS. So we have a water wet system. The capillary number is around 10 to the -6. It means that you are working with capillary dominate regime. So capillary forces are dominant on the system. This is an example. This experiment is really interesting, in fact, because it is similar to a situation that can be found in an oil reservoir and based with some carbonate rocks, because in majority of the cases, carbonate rocks are oil wet. So the water in this situation it will present a similar behavior that you'll be seeing if you have oil in the same condition, the oil saturating the system, the porous space. Here you have, for comparison, some a micromodel without any kind of microporosity. Here you can see the experiment we have carried out. So in this case, we have a movie, a 10 times faster movie than the real time. So as you can see, the interface is stable. There is no well-defined preferential fluid flow in this case. Most of the trapped oil is found in the transversal channels to the direction of the fluid flow, as you can see here. The residual saturation in this case is around 10%. This situation presents some microporous grains in the system. So you can see the flow interface is stable in the similar way that before. It's interesting to see that no fluid was displaced from the microporous regions. So we can see some residual saturation associated to the macro channels in the same way. So here we have residual saturation associated to the microporous regions, but we have also some residual saturation to the big channels too. In this case, the residual saturation is around 43%. Here, the case with some microporous grains and a microporous matrix filling a part of the channels, the big channels. So there is a more defined preferential fluid flow, but in this case, you can see a considerable part from the water in the microporous regimes could be drained in the process. So some saturating fluid was displayed from the microporous micro regimes, as I said, but a great amount remains in those regimes. So In the same way as before, some residual fluid is found in the transversal channels, in the that macroscopic channels. In this case, residual fluid saturation is around 46%. Here, the last case, which considers the presence of vugs, big channels in the system, together with some microporous matrix. It's really interesting to see here that almost all fluid in the vugs was displaced. And but at the end of the process, you have some residual fluid mainly trapped in the microchannels. In this case, just a small amount is found in the vugs in this situation. As you can see here, the saturation, the residual fluid saturation, the residual water saturation is around 17%. Here you have a general view of the dependence, of the influence of the microporous arrangement in the system, considering initially 100% saturated water system, and after the drainage process. So you can see that depending on the position of the arrangement of the microporosity, you can reach different results. Has some conclusions we have that you have seen that micromodel approach is a really interesting tool to analyze the mechanisms occurring at porous scale. So you have seen that permeability is strongly related to the arrangement of the microporosity in the system. Microporosity added to drains will raise the permeability. Otherwise, when it is present in the macroscopic channels as microporous matrix, we will see the permeability goes down. The type of microporosity has an important influence on the residual fluid saturation. A significant amount of trapped fluid is found in the microporous regimes for drainage process. And a higher microporous matrix content can lead to higher sweeping efficiency of the fluid stored in vugs. So this is my presentation. I would like to thank you for your attention. If you wish, you can send me an email with any question. Thank you again for inviting me and in the organization of this prestigious event. And additionally, I would like to thank Petrobras for a so important financial support. Thank you very much.
Okay, Fabiano, thank you very, very much for the talk. Well, finally, we are heading to the final session, which is related to discussions. So, Abreu, would you like to chair this with me and also Alexei?
Yes.
Or?
Yes, you and me and Gregory, not Alexei.
Gregory, okay.
Okay.
So following the same format of the previous discussions, people who want to pose questions can either unmute themselves or raise hands, and we will transfer for the word for the question. Okay.
Marcia, I have a question. I can start.
Yes, Marcia, go ahead.
Okay, I have a question for Sujit. Were you able to, when you have the pore dependent transition, can you correlate that with the geometry of the pore? What I'm thinking is that if you have a pore where you have a stronger extensional flow, does it go through the instability at at a lower flow rate? Or so can you relate the distribution to the geometry? Because when you show the different pores, it seems that the more extension dominated pore were becoming stable earlier.
That is a fantastic point. That is an excellent point. In fact, that's probably the biggest question that we're trying to pursue at the moment.
Mm-hmm.
And you're completely, I mean, your intuition, I think is completely spot on. That's indeed our operating hypothesis.
Okay.
And in particular, so, as I mentioned, we map out the 3D pore space structure. Of course, the 3D geometry of each pore is very complex. There are many different geometric descriptors. And so, we've tried looking at the potential correlation between that critical Weisenberg number that you mentioned. And for example, just basic things like the aspect ratio, like the ratio between the pore throat size and the pore body size, for example, which is related to how extensional that flow is. We haven't seen much of a correlation there yet. We're trying to relate it to other things like just the size of the pore. We haven't found any strong correlations yet, but that's something that's exactly what we're trying to do now. One interesting piece of this puzzle is, you mentioned the extension being important here, which is exactly the case. Something that we've been thinking about is, depending on the geometry of the pore locally, stagnation points can arise in the flow. So for example, just regions where the flow kind of diverges and you get a local stagnation point. And at stagnation points, you can get very strong stretching and elongation. And so one question is, perhaps is it related to the incidence of stagnation points? And so that's something that we're trying to do. I don't have a good answer to that yet, but that's, I think, probably the most important question at this point that we're trying to address. And that's something that, we're open to any suggestions. I think at the end of the day, my dream, which is kind of along the lines of what you mentioned, my dream is, if we can deduce what that distribution of critical Weisenberg numbers is just by looking at a porous medium, right? For example, you take your whatever core that you want, do an X-ray CT map or whatever of it, get the pore space structure, and then somehow be able to deduce from that pore space mapping what the distribution of different flow rates or Weisenberg numbers at which the different pores become unstable is, then you could, knowing the polymer rheology, essentially plug that into our model and in principle deduce what the final macroscopic flow behavior would be. That would be super cool. That's kind of the long-term dream that we're working towards, but it's steady progress. We don't have any clear answers yet, but it's a really great point.
And a related question, Sujit, and then I'll leave for other people to ask more. So
I have a question for you as well. Okay. So I'll jump in afterwards.
So if you run the same experiment with different size of your glass beads, so you would change a little bit your pore geometry. So the transition will probably shift, will it not? Or
that's a great question. So we do have, we have measurements on different pore size media. I showed you just one example, but we've done that for different media where the distribution or the pore size distribution is the same, but it's shifted. It's rescaled, and we see very similar behavior, except exactly as you said, the transitions are shifted when you incorporate the effective pore size through defining the Weisenberg number correctly. That's defined using the characteristic interstitial shear rate, which depends on the mean pore size. When you do that, everything collapses beautifully. Okay, and so I didn't show those data, but we do have those data. And actually that's part of a follow-up work that we're putting together right now. So it seems like what I presented is fairly, is more general than what I showed today.
Okay, great. Thank you.
Great point. Thank you. If the moderator will allow it, I have a quick question for Marcio.
Sure. Go ahead.
Yeah, well, I mean, I loved your talk. You know, the ideas are really beautiful. I just had a quick question about these capsules, which you showed really nicely the mechanical characterization of it. My question is, are those permeable? That is to say, you know, you talked about how you use a polymer to make that shell.
Mhm.
Is there any kind of permeability of that polymer? And if so, does that influence the mechanics in any way? And the reason why I ask is because, you know, something that we studied a long time ago is when you have a permeable shell, then the viscous pressure drop across that shell of just trying to force fluid out can also play a role. So I'm curious if that's something that manifests in the experiments you guys have done.
Yeah, so they are permeable somehow because we are able to, I'm sorry, not for this. So we have worked with different capsules. The one that I showed you were made of gel and gum, the capsule. So we haven't done any experiments on permeability through the shell. We have run experiments with the same capsule flowing through constriction, and we get more or less the same result. So maybe even if they're permeable, the pressure difference that we get is not strong enough, and the residence time is not long enough to drive liquid out of the inside of the shell. But probably there is some permeability on the polymer matrix, but maybe not on the level that would be an issue for us.
That makes sense. Thank you.
I have a quick question. Can I go ahead?
Yes, go ahead.
Please go ahead.
Marcel.
Okay, to Sujit. Hi, Sujit, again. Very nice presentation as always. I was wondering, so you showed this this PIV image, right? This is in a plane, right? It's confocal microscopy, but this is a three-dimensional porous medium, so the flow is not two-dimensional. So what's the effect of the out-of-plane velocity fields there, or could you pick up some pores where you could perhaps, I don't know if by luck or by construction, have the flow in the field, in the plane of the pore?
Great point. And great point. And good to see you again, Marcel. So I think that's a great point. So that's where the being able to, you know, visualize in 3D at different depths is really important. You're completely right that we're just taking a 2D slice of a 3D velocity field. So we're capturing the X, Y velocity components, but there is a Z component, and typically that Z component is non-negligible. You know, especially in these chaotic flows, there's all sorts of stuff going on. So that is non-negligible. However, and so, you know, and we can, you know, image at different depths, but that still doesn't give us that Z component. It just tells us how the XY field changes spatially. However, what we do in our experiments is we make sure that we're deep enough inside so that, you know, the flow field, as you pointed out, is three-dimensional. We're taking a section, a 2D slice through that 3D flow field. And in all of our calculations, what we do is we assume that locally within that pore, basically it's isotropic, except for, of course, that imposed flow direction. And so we essentially put in an additional factor to represent that third dimension into our analysis. But all of our analysis is kind of agnostic to that point. You know, whether or not a pore is stable or unstable, you can tell pretty straightforward just from the 2D flow field. That being said, we are trying to access that Z component of the velocity field. One way to do it, you know, people have come up with computational ways of doing it just based on mass conservation. You know, you have the 2D flow field, you know that the stuff coming in 3D is the stuff coming out. So there are computational ways of trying to infer that. We're also trying to use holography to get that Z component. But at the moment, we're just looking at a 2D slice of that 3D flow field. And so far, it seems like that hasn't been a huge limitation yet. But that is something we're interested in doing. I hope that answers your question. Basically, it's a good point. We don't think it influences any of our findings yet, but it is something we're interested in trying to extract in our future work.
Super. Thanks a lot.
Thank you.
Grigori, Abreu, I have a couple of questions to
Please.
both Suji and Marcio.
Go ahead, Márcio.
So I ask first Suji. So very, very nice talk. I enjoyed very much. Very interesting. So I have a couple of questions. One is regarding the concept that you postulate, which is this elastic turbulence. I was trying to do a parallel of this concept with the classical turbulence. I know they are very different. Usually, mathematically, turbulence, if you just write the Navier-Stokes equation, the turbulence, when you increase the Reynolds number, you can show that any perturbations you do in the velocity field, if the Reynolds number is very small, they can die out. If the Reynolds number grows, they can give rise to the turbulence. So since your case, this concept is very different, how could you explain this in terms of fluctuations if you just look at the mathematical structure of the Navier-Stokes equations?
That is a great, yeah.
Yes.
That is a great question. Thank you for asking that question. And so I'll try to elaborate that, but maybe I'll plug a paper that we put together actually. So we didn't invent the concept of elastic turbulence. It's something people have studied for several years now. And we actually, so I organized a workshop with where we focused on this question among many other questions that you just asked. And we actually have a review article describing all of those details that we're going to put on the archive within the next week or two. So, I'll just mention that if any of you are interested, we talk about the full, mathematical details of that in that article. So I encourage you to take a look at that. But in a nutshell, I'll mention, so if you take the Navier-Stokes equation, throw out the inertial terms, because for the flows that we're looking at, inertia doesn't play a role. The Reynolds numbers are all smaller than 1. So if you take the Stokes equation and then add an additional contribution arising from the polymer elastic stresses, right? Because you have stresses due to the polymer. It turns out that, you mentioned the Reynolds number. It turns out that when you take the Stokes equation with the added component of the polymer elastic stresses, you get the Weisenberg number, which is this number that I talked about. You actually get the Weisenberg number instead of the Reynolds number. And that similarly, people have shown that if you do, for example, a linear stability analysis, just as you mentioned for inertial turbulence, but now for the Stokes equation with the polymeric stresses, what you find is actually that Weisenberg number, similar to what you mentioned for inertial turbulence, that depending on the value of that Weisenberg number, if that Weisenberg number is above a threshold value, then just as in inertial turbulence, perturbations in the flow get amplified and you get elastic turbulence. So it's actually very similar mathematically to the case of inertial turbulence that you mentioned, except now the control parameter is not the Reynolds number, it's the Weisenberg number.
Okay.
Now, of course, there's the question, another question related to what you mentioned, which is, what is the origin of those perturbations kicking the flow? And in a porous medium, the origin of that is fairly clear. It's the fact that you have all these obstacles and you have the curvature in the streamline that the fluid has to move around. And so that's what the source of that perturbation is. But mathematically, the mapping to inertial turbulence is actually very similar to the math that describes elastic turbulence, but you replace the Reynolds number with a Weisenberg number.
Okay. Thank you very much. Very nice.
Yeah.
Okay. Go ahead, Alexei.
If I can interfere, just
Sure.
question. What you just said to me, will it be correct if I say that this phenomena resembles flutter in air elasticity even more than turbulence, I would say?
You know, that's an interesting question. I have to admit, I don't know enough about Flutter to answer that question in an intelligent
But
way.
it's an instability of elastic structures
Yeah.
interacting with fluid, essentially.
Yeah. No, it's an interesting point. I'm familiar with it. I just don't know it deep enough to be able to give you a definitive answer, but that's an interesting analogy, and there might indeed be a deep connection there. I'm not sure. Yeah, it's a good point.
And the second question also I think Marcel Moura has raised his hand too.
Yeah, I have a question, but you can go ahead. I take it after you.
Okay. Concerning your polymer adsorption in the tiny pores, I believe that the charges, electrical charges, will play a very important role. So, for instance, if the polymer is a cationic polymer and the surface is negatively charged, then they are going to bound. So you think that this polymer elasticity, when it is absorbed, will be strongly a function of the electric charge at the surface of the macromolecule?
So that's another really important point. The polymer that we use is partially hydrolyzed polyacrylamide. Typically, there is a lot of salt in the background solution. So, we add a lot of salt, which tends to screen electrostatic interactions. But you're completely right. In our case, the solid matrix is borosilicate glass, which is negatively charged, right? The polymer is partially hydrolyzed polyacrylamide. In our experiments, we don't see significant adsorption, but of course, as you point out, that will be sensitive to the polymer chemistry, the salt content of your solution, and the chemistry of your solid matrix. So indeed, there will be scenarios, I'm sure, in which adsorption to the solid matrix will be important and will play a role. In our experiments, we made sure to control for that. And, our main kind of result is that you don't need that to be able to, describe the macroscopic flow resistance and this increase in the flow resistance. That being said, adsorption, I think, will certainly play a role depending on the chemistry of your particular application. And that's another factor to take into account, certainly. But in our experiments, it did not play an appreciable role. But that doesn't mean it doesn't always play a role.
Okay, thank you.
Thank you.
So,
Okay.
Marcel?
Right. So it's a question to Marcio. So Marcio, you showed how you could, with this microparticles, how that there was like a range of diameters and of thicknesses of the layer around the particles that would maximize the blockage, right, for a given porous material that has a given pore size. So if you have like a real pore sample with a distribution of pore throat sizes, could you engineer this a distribution of these capsules so that maybe the porous medium would be like you could get a distribution that maximizes the oil recovery for a given porous medium?
Yeah, so this is actually what we are working on. So there are two, let's say, challenges. One, we started, like what I was showing to you was kind of like a proof of concept, because we have a very homogeneous porous media, monodispersed capsule. So we knew exactly the mechanical response for each capsule. So now we are trying to inject these capsules through an actual rock core, a sandstone, which is still fairly uniform, but there is some distribution on the pore size. And I would say the mean pore throat size of the sandstone we are injecting is around between 15 and 20 micrometer. So one big challenge is to make capsules at that size, not 100 micrometer on the range of 20 micrometer, which is not easy. So we are trying different avenues, and and also if what happens if we have a distribution of the size of the microcapsule. So we are working on this now. But hopefully, I think when you inject water would go through the larger pore. It will go through the easy way out. So my feeling is that we need to design the capsule to be able to block the large pores. Otherwise, you're going to clog the whole thing. So that's the risk is to lose the injectivity. It's basically to clog everything, and then you want your capsule to go deep in your porous media, not be just filtered in the beginning. So I think that's the challenge.
Right. And just a quick follow-up question. So you showed the cases of the capsules that quite didn't work for what you wanted, the ones that broke apart, right?
Mm-hmm.
But could there be any applications where this could actually be used for?
Yes.
That you could like deliver some
exactly
material inside
so,
the porous medium? Or...
Yeah, another area of research we have in the lab is to use capsule for control target delivery. So we've been working with pH to have like gastro-resistant capsule, so capsules that are burst by pH changes or osmotic pressure. And one way that you can control also the burst of a capsule is by force, by shear stress. So these capsules, the one that bursts, would be a good candidate for target delivery in a reservoir. So then you would design the capsule to break at certain conditions. Yes. I don't know if you remember in the plot, I didn't mention that because of time. I was saying that I didn't say that these are not the capsules that don't work. I say these are the capsules that are good for target delivery because it's just a different application. Yes.
Super. Thanks a lot.
Thank you, Marcel.
I think Grigory has one question. Grigory has raised his hand.
Yeah. Well, I will try to make a connection. So today morning, we saw a lot of talks about oil recovery. And of course, we are interested in macro scales. So, and now we saw 4 very interesting talks about these microfluidic models. And I'm amazed with all these microfluidics. I discovered it very recently. And I'm still in love with this because we can actually see what we are simulating and calculating. But the question is, which information in your opinion, we can directly bring from microfluidics to the field scale? So I will address question to Marcio, but I will be very happy if Sujit, Aurora, and Fabiano can add something.
So I'll start. I'll be quick, so other people can give their opinion. I think that the main point of the microfluidics is to really understand the physics, because I think if you understand the physics, you can design your system, your complex flow in a more efficient way. So I think Sujit's talk is a very good example. So what should be the rheological properties of your polymer solution to get this effect on the residual oil? So it has to do with the elasticity. And so I think it's the main goal of this microfluidics is to really go after the physics, and then you can design your fluids to act as they are supposed to act. And then for sure you go to the macro scale and test to see if it works or not. So the same thing applies to the foam work that I was showing. So what type of foam or what's the level of surfactant solution that you need in order to get a certain number of lamella formed such that you block the flow. So that's my view of the use of microfluidics.
So just following up. So you think it's only basic physics, so basic science, not nothing numerically, nothing quantitatively we can bring to bigger scale or to different materials?
No, we've used microfluidics, for example, to measure let's say relative permeability, all these like macroscopic function that go in as input in models. But most microfluidics, in order for you to visualize well and see all the details, the pore size are usually larger than what you would see in a real rock. So I think the scale is not perfect 1-to-1. So that's why I think it's more a fundamental physics, and then you go from that understanding, develop continuous model that you can go on a macro scale type model.
I have a question for everyone here, Majid. Sorry to Marcio and Suji in the same direction. It seems to me that there is a PDE hidden, because it seems that Navier-Stokes not enough And I'd like to see some words about that, because it seems to me that there is some PDE hidden with a new effect, maybe.
Grigori, sorry. Go
Yes.
ahead.
Well, I
Go ahead.
was just gonna just very quickly jump in and you know, both to Gregory's to both points. You know, I think Marcio described it very nicely. You know, when he said that the pore scale observations really kind of give us an idea of the physics, and it kind of informs how we upscale to macroscopic models. You know, you mentioned there's a PD hidden, right? So we know that in each pore, Navier-Stokes equation works, right? I mean, it must. But in reality, you're not going to simulate Navier-Stokes equation in an entire reservoir, in every single pore of a reservoir, right? And so, and we also know that if you look at large enough representative elementary volumes, right, at a large enough scale, then you can just use Darcy's law with the right effective parameters, the right permeability, relative permeability, viscosity, etc. The question is, how do you go from, you know, how do you link one to the other, and over what length scales is it appropriate to do so? And I think that really figuring out that link and figuring out when you can do it and at what scales, length scales, time scales, as Marcio was saying, that's really where I think the power of microfluidic and pore scale imaging is useful. You know, you can measure something at large scales and put that into your reservoir simulator and get stuff out. The question is, how general is that going to be? How general are your results going to be? Are they going to be applicable in another porous medium with a different structure or chemistry? Are they going to be applicable if you use a different fluid? It's hard to develop generalizable insights from purely empirical macroscopic models. Similarly, from pore scale imaging, you know, it's very challenging to be able to say, okay, I know what's going on in one pore, therefore now I can model everything, right? And the challenge is in linking the two together. And, you know, that was really the big motivation for the work that I presented, where, you know, we wanted to be able to directly link what's going on in a pore to the structure of the porous medium, to the overall macroscopic transport. And I see that, you know, and also Marcio discussed that very nicely. I see that as being really the opportunity for the future for us in this field, is to use a better understanding of pore scale physics to come up with, you know, intelligent and creative ways to upscale and figure out when, at what length scales are those upscaling procedures appropriate, and how to do them in the most accurate way. I hope that was a long-winded answer to a short question, but I hope that was useful.
Thanks.
Murad, go ahead.
No. I think Suji told what I was thinking about of telling. No, I can give an example, Grigory. This, for instance, a very straightforward case. This apparent viscosity, it is a macroscopic property where you can plug into the simulators. No? Right? It's a viscosity of water with polymers, no, of a water polymer solution. So it's an example that you can use the pore scale physics and then come up with something that you can plug in the simulator.
And that was the motivation for our work, is, you know, people have been studying polymer physics for decades, right? And people have been using polymers in the field for decades. And then when we were reading the literature and trying to do our experiments, we were shocked that the most basic macroscopic descriptor, the apparent viscosity, we still don't have a very good way to predict it generally, or to, you know, describe why it is what it is. And that was really shocking to us. And that was the motivation for the work that we did. And I think we will have opportunities, you know, the beautiful work that Marcio presented, other people presented, you know, I think trying to link those two will be a real opportunity for the future.
just jumping in, I think that applies in different physics. So what Fabiano showed, so you have all these two double permeability, double porosity models that you have a bunch of parameters to link. So like the type of visualization that Fabiano showed with the micropore and macropores could be used to get these macroscopic parameters of the double porosity, double permeability models and things like that. So I think that's the main benefit of microfluidics and I would say mesoscale modeling, even like pore network models and these types of things.
So you think for double porosity models, we can like, well, Fabiano is not answering, but so we can actually take out something numeric, something quantitatively to quantitative information.
You can upscale the shape factor, no? For instance, which appears in the transfer function.
Exactly. So from what Fabiano was showing, he shows exactly like how much of the fluid was displaced from the macropore or the micropore. So that would go to the transfer functions on functions. Yes.
That's right. Sometimes when you can use that information to study, to establish some theoretical model to predict the permeability is something interesting to that. We have observed that when we consider the presence of microporous regimes in the system, it's not possible to use that conventional models very used as a Cosigny model. It doesn't work for that situation. So it's important to think a little more how it's possible to extrapolate that information. And the next months, we would like to use the conventional models in this situation and in which we have two scales present and representing some important effects on the system. So I think it's really important, and it can be used in a macro scale, in a reservoir scale, if you want.
Thank you.
And how about of the effect of hysteresis in this situation? Could someone please make some comments about that? If it's possible, some connection with the mathematical model. Please, Suji, go ahead.
Well, I mean, I think, hysteresis is the word that strikes fear into many people's hearts, but is important to think about. I don't know if I have anything intelligent to say other than, it's very situation dependent. Right? In some cases, hysteresis is important. You have to consider the full history of whatever you injected and what your flow was. In some cases, it doesn't seem to matter. Especially in relative permeability and relative permeability measurements, hysteresis often plays a huge role because it changes the configurations of the fluids, and that, can have a significant impact. In other cases, for example, in the measurements I talked about today with the polymers, we actually did not measure any hysteresis. I didn't show that, but we weren't able to measure any significant hysteresis. So in some cases, it's relevant. In some cases, it's not. I don't know if I have anything more intelligent to say other than that is certainly an important factor, and it's important both in pore scale studies and macroscopic studies to quantify that and see if that is something that needs to be considered or not. It complicates things, it complicates our models and our interpretation, but if it's there, then it's there, and we have to be able to consider it. So I don't really have anything to say other than I think it's a very important point and something to think about.
No, great. That was my point in that question that I made to Paddy, because hysteresis does affect the mobility, with then the fractional flow functions, and when you couple with the pressure equation, you should take into account in the transmissibility. So in some sense, you should take all the micro scales from the micro scale, and this situation is not so easy, because for the hyperbolic viewpoint, the the hyperbolic equation are really hard to solve. There is no theory from the hyperbolic viewpoint. And there are some very interesting connection in this way. Márcio?
Yes, I have one question to Márcio Carvalho. Márcio, can you show your slide where you write the Navier-Stokes equation and the solid mechanics for the capsule at the pore level? I'm curious about how do you close this model?
Are you seeing my slide already, or?
Yes, I can see your first slide. Yeah, your slide.
Okay, I'm getting there.
If you can put
this one.
I can't see in the column. If you can just click and show in the yes.
Okay, so
this one. Okay.
I probably don't have the whole model here because it's I probably took some of the material out to fit in one slide. So, but the idea is that you have the Navier-Stokes equation, and then you create like a body force that's associated the force that the solid phase is making in the fluid phase. Okay.
Okay.
And this force is basically the net force that's acting on this membrane.
Okay, I got it.
You can write this.
I thought it was some sort of boundary conditions, but no, you treat the sphere as something which is interacting with the free flow in all points.
Yeah. So the point is that I'm using a simple elastic model that is just like a shell equation. So it's a one-dimensional model that there is a tension along the shell. So the surface divergence of this tension is the net force that's acting on the shell. And then for it to be in equilibrium, that force comes from the fluid. That's what's equilibrating this. So at the end, in terms of the finite element model, when I have the weighted residual of the Navier-Stokes equation, I need to integrate this, but this is only acting along this line, this one-dimensional model. So I have to, the area integral of this force becomes a line integral. So then I have, so whenever I'm with a residue that has this one-dimensional solid domain inside that element, I need to add the line integral for that weighted residual.
Okay. So you have also a mesh for the free flow inside the capsule, because you're going to have the coupling of the 1G with the 2G, which is the body force, but then inside the capsule,
it's a liquid here too.
What?
It's so for us, to make it simple, the model, we assume that the viscosity inside is equal to the viscosity outside. I'm solving for the velocity field on the inside of the capsule also. So if you, so I solve velocity and pressure field. In this case, I'm just showing the pressure field, but you can see that I calculate the pressure distribution inside the capsule from the solving the Navier-Stokes equation, the continuity equation. To make it simple, we consider the viscosity to be the same, but otherwise I would have to have like a marker function to know that if I'm in one side or the other of my one dimension, so it would just be another variable that I would have to track.
Okay, and what sort of boundary conditions you consider between the shell and the bottom boundary? Is like a friction?
Well,
it's
here,
like
no.
A friction.
So it's like a symmetry, because this is a symmetry plane.
Okay, it's a symmetry.
So it's like a symmetry condition on both ends. Yeah.
Okay, I got it. Thank you.
You're welcome.
I thought you were doing some sort of domain decomposition. No, one part solved for the 1G, but no, you treat in terms of a body force. Okay.
Yes, so we couple everything, and then the one-dimensional mesh for the solid part gets convected by the fluid velocity.
By the flow velocity.
And that's why if I share my slide here, it's not always good, because so if I go back to my slide, the last plot on the right This is the area inside the capsule. So we need to track to make sure that we're not losing mass.
Okay. Now I can see. I could not see before, but now I can see.
So this is like tracking the area inside the capsule, because I'm compacting this one-dimensional mesh through the fixed two-dimensional mesh for the flow. So one of the limitations for such a model is that you may have a fluid, a net flow through that boundary, because nowhere I impose that n dot v has to be equal to the velocity there. So that's why we need to track how much mass loss. And this one here in this case was pretty good. You see, well, I think we lost in this case like less than 0.5% of the mass. So depending on the discretization, both in space and time, you could, like this bubble, I can make the capsule disappear with time, because it's losing so much mass that it goes away, because the simulation is very inaccurate. So we need to control the discretization to be able to conserve mass.
Okay, got it. And these shell equations you are solving, they are in very large strains. You're not
so we use
any sort of...
So we use 3 different models. We started with just a simple Hookean model, but then which is probably not valid for the level of deformation. Then we use a neo-Hookean model. We also use what's called a Scalac model, which is good to mimic like a cell behavior, a cell membrane behavior, and things like that. So we test these 3 models.
Okay.
Marcel,
the results that I'm showing here was for neo-Hookean.
Okay, for the neo-Hookean. Okay.
Marcel?
Yes, I have a quick question to Aurora. Could you just comment if there are flows inside the films that make up the foam, and if these flows are stabilizing or destabilizing to the foam? They tend to go like to some place where the foam is locally thicker to somewhere where it's thinner, so it stabilizes.
You mean flow in between the bubbles?
Yes, well, exactly. Yeah.
Yes. Well, in the microfluidic experiment, we couldn't see that. It's very difficult to see, as Marcia says, the size that you have. You need to put like you need to design an experiment for that, like to put something that you can visualize or follow. But that's an interesting point, because you can have that either with the nanoparticles that can be in there. It has been reported that if you have high concentrations of nanoparticles, they might not all absorb at the lamellas, at the interface, and then they may remain in that liquid in between, and it could happen. But it also it can be also dependent on the surfactant type. We have also some experiments with that form different aggregates with surfactants, not only micelles, but we can have like these kind of viscoelastic surfactants. Similar, I was even going to ask Sujit if they try also with surfactants besides with the polymers, because it's a similar component, but you have these giant micelles that can increase viscosity and also act, well, it will confer viscoelastic properties to the liquid phase, not just to the foam that has it per se. And in that case, there may be some turbulence as well, because these are larger structures, but we need to design that experiment. In our case, we are users of microfluidics. So we are happy to do any collaboration with the chemistry and engineering that we have behind. We have many options for visualizing, but just also joining a bit of what Grigory asked about the usefulness of this for macro application and modeling. We believe that it has a lot of importance and relevance, because even when we defend a lot the bulk behavior in the case of foams, it has, you cannot correlate directly with the behavior when it's in confinement. So you can see some of the mechanisms and then transfer, because the chemical compounds will be the same and the structures will be the same in bulk than in porous media. So in that case, you can correlate. but in terms of flow and the behavior of these bubbles will be different. But the other thing is that that is interesting of that question is how you need to define very well the ratio between the size of the channel and the size of the bubbles you have. Because you have like very small bubbles, which is possible when you have very low interfacial tension, for example, and nitrogen gas, which is very stable. Then you might not get this in larger channels, like in microporous devices. You might not have a bubble train properly. What we saw is that in some of the pores you have several bubbles, more similar to the 3D structure, only that in 2D, this array of bubbles. But when you have something like with higher surface tension, then it tends to expand and it's limited by the channel. So in the other case, turbulence will make more sense because you will have more liquid phase in there. When you have like these large bubbles in a train flowing through a channel, I don't think that will make that much relevance. It will be more important in terms of the stability of the portion. But anyways, right. It's very interesting. Yeah. This as I say, I'm a user, so I cannot contribute much in the mathematical part of the microfluidics, but for offering quality data for the calculations and trying to bring together the chemistry behind that, or the physical chemistry that determines that physical behavior, we are open for collaborations.
Great, thank you. I can imagine it's probably a very, very hard problem to image. I mean, imaging particles in the bulk of liquids is already hard enough. To image particles like inside that tiny membrane or like the two sides of
and imaging particles in turbulence will be even more difficult because just that we are working as well, like Mars is working as well. We are working in trying to visualize those particles, but studying turbulence at the same time, I think is difficult. Perhaps we can design other type of experiments, and not necessarily with nanoparticles, but with these aggregates of surfactants, which we can easily get some fluorescent tag in there, and it perhaps will be easier to see that.
Right. Thank you.
So we have time for questions, comments, please.
Well, if know anyone, I will make a common joke. Aurora, next time we can try to see turbulence on the surface of the bubble. Because actually I saw some papers about it, so maybe it's something non-trivial to see.
Yes, Gregory, but you see, we need another lab for that. As I say, we cannot, it's very difficult to work. For us, has been a challenge to go into the micro world with the micro channeling, because in our lab, we have had to work with all the levels, like pore level and macro level. Like we have the core flooding and the bulk foam, and you need a specialized equipment for that. It's not so simple, but I believe it is possible, just with a good camera, especially. But we can try to do that. But viscosity on the surface, I think I mentioned in some part just the word, at least of my talk, interfacial viscosity is very important, not only the viscosity in bulk. So in that case, that turbulence that you are talking about on the surface of the bubble may have to do with the interfacial viscosity, the viscous behavior of that interfacial film that is at the end, which determines the stability of that bubble. And the ability, the elasticity of that film determines how it can be regenerated in a porous medium. because I found that fascinating of using microfluidics is the opportunity to see not only formation and destruction, but the actual mechanism that helps to transport, in the case of foam, through the porous media, which is regeneration after passing through each pore throat. And in that case, the viscous component is as important as the elastic component of the surface of the bubble, which is a liquid, of course. So it might have turbulence as well.
Grigori, I have a question to Aurora to follow up on what she was saying now. So can you measure the interface viscosity of your systems when you put the nanoparticles or when you mix the CO2 with the nitrogen? Can you, because from what I understood, you did the stability of the foam, the study of the stability, both in the bulk, in the porous, on the micro model. So, but can you go to a tensiometer and actually try to measure the interfacial viscosity for these different systems?
It's possible to do with the drop oscillatory system. We don't
dependent drop.
Yes, yeah, in that we didn't have the accessory, and now we bought it. We hopefully will go into that. But it is it's also tricky experiment, Marcio, because you might need to change the conditions because you need to go to extreme changes in interfacial tension. If you have a lot of either nanoparticles or surfactant, like you do for the microfluidics and the bulk experiments, then you won't see much changes when you oscillate because you will always have like a supply of components. And this elasticity and viscosity, well, viscosity is more related to the structures that you have in that film. But in the case of elasticity, it has a lot to do with the migration of components, either preferentially within the interfacial film, but it might be hindered by migration from the bulk phase. So we haven't done the experiments yet, but we are going to. We intend to. That's easier than the turbulence that Grigori wants,
yeah.
at least. but it's. These experiments, I believe they are very important to understand these mechanisms within the pores of making a bubble and breaking it. And then, of course, that's at pore level. Even when you are seeing one bubble, it's important. But then you go to the different scales, and that's what determines the flow and the physical properties within. And then
the behavior of the micro bubble is going to be different than the behavior of the millimeter size bubble that you get in your tensiometer. So there is still this one more challenge, but I think it would be nice to see the changes in the interfacial viscosity if you can measure.
Yes, I believe that if you are able to correlate that behavior with the curvature, the angle of the droplets, even if you are working in the tensiometer, you can then correlate with the different
size.
Yes, that you have in the micromodel. But it's interesting as well, for example, to have experiments with different micromodels with different sizes. Then you perhaps a systematic study if you have like different chips that you can control the size of the channel. This elasticity can be directly correlated to how the bubble can reform. Because what we have seen is that the bubble enters, I didn't mention because it's also a matter of time, but the bubble enters very small in the channel. And then if it doesn't have enough protection, like in the case of certain surfactants or nanoparticles, it grows and then it stops. But that doesn't mean that the bubble is going to break, because the lamella might still hold it. But the distribution changes, and that changes the mobility. The size distribution. Anyways. So, but I don't know how to model that. So that I leave for the mathematicians, that part.
Oh, pretty nice. Are there any other questions, comments?
I have a quick one to
please go ahead,
Fabiano. Fabiano still around? I think he is,
Okay.
right? You showed this drainage experiments, right, with this dual porosity systems. I was wondering, would it be possible to do imbibition?
Yes, it's possible to do imbibition. We have tried to find a liquid, a suitable liquid to use in this case, because it's not so easy, in fact. But I have tried some ones, but until this moment, we haven't found one appropriate for that situation. So, but I think it will be really interesting, because one side we have a drainage process, and we could see that the microporosity is really important under that circumstance, because the residual oil is residual fluid is associated especially to the microporosity regimes. But in this case, in the imbibition case, I think the process will be completely different. I think, in my opinion, because the injecting the displacing fluid can, so in this way, displace the fluid from the microporous regimes. So I think we are not going to have some fluid in that case. So I think the displacement, the immiscible displacement, will be very efficient considering that situation. Nice, very interesting question, in fact. But it's something that you need to try more, because PDMS is not a so good solid to work with different fluids. In some kind, PDMS can absorb some substances. So we cannot use hydrocarbons with PDMS, because it absorbs and swell during the experiment, especially when you are considering longer experiments. So if you have a quick, if you have the intention to perform a quick experiment, you can use hydrocarbon fluid. But if not, you cannot. You cannot use for that purpose.
So if you just use like a regular oil, like kitchen oil, would you expect PDMS to react to it, to absorb it, or does that happen with PDMS?
You mentioned what kind of fluid?
If you use like a regular kitchen oil, like cooking oil, sunflower oil, or any of the regular oils that we buy on the supermarket,
okay,
does PDMS react to them? Does it is it known that it absorbs?
I don't know. I don't know. In this case,
okay.
I'm sorry. I can.
I'm
asking just out of curiosity, because I never worked with PDMS.
So we have been using PDMS for some experiments now. So mineral oil typically works well with PDMS.
Works well. Mm-hmm.
Yeah. And then if you can treat with PVA, it's also a good way to change the wettability of it, to make it water wet.
In fact, one problem that we have found in our experiments is the need of having a lot of micromodules available for the experiments. So because sometimes after some experiment, it's impossible to clean completely the micromodule and to recover the same state it had before. So in each experiment, if you use a oil, for example, a oil like this one, probably you're gonna have you will not be able to use more that micromodule. So you need one more. So when you are interested in doing some statistical analysis, you need a lot of them. So and it can become the process a little bit more expensive, but it's possible. But you said about mineral oil. I will try that. I will try that. It's interesting.
So Marcio, did you mention that PVA can be used for wettability alteration of PDMS? Is it just flushing PVA through it?
Yeah, it lasts for a while. It's not eternal, but it lasts for a while. Yeah. I can send you some of the things we've been doing in this sense.
That'll be good.
Yeah.
I saw something about plasma treatment being effective in PDMS I don't know exactly how it goes, but it's a physical process, plasma treatment.
Yeah.
This is not the same thing as this PVA flushing, right?
PVA is a poor man solution. It's
Right.
simpler. The
If
plasma
it works, it
probably-
works.
Yeah, no, it works, but not for a long time. But it works for maybe for, I don't know, a week or so.
Right.
I can get you the procedure that we are using.
That'd be great.
So we are going to the end of this Brazilian chapter meeting, but before ending, I would like to take advantage of this audience, all the speakers, the participants, to feedback about the format of this meeting. If something that you think that we should do, maybe next time, maybe a final round of comments, and then I will close the event. But before, I'd like to hear some words on that, if there are any, please.
I've been speaking
Everybody
a lot
happy?
already, but I can
happy?
comment. I think this
Please go
worked
ahead.
very, very well. I mean, I think we all have many reasons to congratulate the organizers. This was super well organized, and I think actually this format. I don't know if you have seen in other conferences. I have myself. I had never seen anything like that, particularly with online conferences. But this format of having the discussion at the end, I think it really works, because it also probably releases a little bit the stress from the speakers of having to finish very quick, because otherwise I don't get any comments on my talk. So I think this really worked well.
Thank you. It was designed for that, but yeah.
Yeah.
I just wanted to second that. I completely agree. I thought this discussion was just fantastic, and all the other discussions were really great.
Okay. So, okay.
Let me share the slides, just not to lose them, because we are closing and I updated the slides. So.
Okay. Okay. Okay.
Yeah, you can continue talking. It's just the background.
So, on behalf as a chair of the Brazilian chapter, I really would like to thank all the 18 speakers. Many thanks for coming to accept our invitation. I really would like to thank all the participants. Massive interest. Hope all of you enjoyed the event. We have a very nice participation from Brazil and abroad. The Brazilian InterPore is a non-profit making independent scientific organization established in 2014, totally free of charge. If you like to receive emails, please send emails to the organizers. We have a list. We are very close to the InterPore International. And our mission here in Brazil is quite simple: spread the Brazilian chapter and the InterPore to academia and industry, and continuous improvement and exchange ideas on natural and industrial porous media system. Next year, in 2022, we expect we will run the Brazilian meeting in Natal, in the northeast of Brazil. Is a beautiful place. We really hope have it presential, or maybe an hybrid, but with presential format. And that's it. Many thanks again. Stay safe, and hope to see you soon, virtually in the next meeting, in Brazil meeting, or around. Thank you.
Thank you,
Thank
everyone.
you, everybody. Thank you,
Thank
everybody.
you.
Thank you.
Thank you to the organizers.
Thank you. Bye bye.
Just to reinforce, invitation for the next year, and Natal is one of the best beaches in Brazil.
I'm glad you said that, Grigory, because otherwise I would be biased.
Yeah, no, just say it. Yeah, just say it. Imagine 2 years of quarantine, and then you have a conference on the best beach of the world. I mean, not pressured at all.
Okay.
Bye-bye.
Thank you, everyone.
Okay,
And
Okay,
thank
bye-bye.
you.
Thank you,
thank you to
everyone.
the organizers.
Bye bye.
Thank
Bye
you.
bye.
Bye-bye.
Bye. Thank you.
Bye.
Have a good week.
Courage and Grigor,